Just a concept. When Arsutanov again proposed a let's call it scaled down system in which he wanted to put antennas in LEO orbit, but they were rotating at Earth rotation, so they were geostationary. And for doing that, he detached the space elevator, but he still balanced at the geostationary orbit. And again, we are talking about something in the range of 90,000 kilometers, because here we are in LEO orbit, and here again, the figure should be a lot longer on that side. Then there was the proposal for electrodynamic system. And the first two were actually, one was the director of a linear accelerator in Chicago, Professor Drell, in 1966. Another article, I don't mention it here, was from Halfen. And another one, the geomagnetic thruster from Moore in 1966. And practically, they are the first one to propose using Lorentz forces to move in orbit. With no detail on anodes and cathodes, they were primarily proposing using photoelectric effect to liberate electrons. Then came my two mentors, actually, Colombo and Grossi. Grossi, in 1973, he was interested in long antenna for broadcasting a very ultra-low frequency, so ULV, ELV, very long wavelength. And Colombo, instead, was mostly interested in deploying something into the thermosphere, the lower thermosphere, and collect data on a portion of the thermosphere where satellite cannot fly, by using, in both cases, the proposal regarded deploying system from the space shuttle, and were, of course, of much more feasible dimension, 20 kilometers for the long antenna, and 90 kilometers for the Colombo proposal. Now, actually, it's always a bit surprising to people who don't work in tethers to see that many tether flights have taken place. At least I counted 23. I may be missing something. Up there, two experiments that NASA did when NASA was very daring. So in the early 60s, they connected the Agena module to another module and spun the system. It was done on connecting them with 30 meters or something that looked like a car safety belt. But coming into our arena, which is where we are working mostly now, which are the electrodynamic system, which are here in green. There were a number of suborbital flights done by Stanford University to test the concept. And then the two big missions, the one that really were generated by Grossi and Colombo, the TSS-1 deployed from the shuttle in 1992, and the TSS-1 reflight, again deployed from the shuttle in 1996. They were both supposed to be 20 kilometers. The first one, as you know, was ruined by a bolt that was too long and had been added at the last minute to reinforce the structure. and they jumped the deployment system, so he only reached 260 meters. But the second one almost deployed completely and collected very useful data. I will show it to you later. But the satellite was lost. It was lost because in the last 400 meters, the insulation was damaged, the tether insulation. Here you see actually, this is TSS-1R. The tether insulation was damaged down here near the space shuttle. The voltage potential was very high, it was 4 kilovolt. So because of the damage in the insulation, the circuit was open, a big spark for a few seconds, cut the tether and lost the satellite. So in the first one, it was indeed retrieved. In the second one, the satellite was lost. Then a number of other missions. I cannot spend too much time, but very interesting was this one, Prof, which was completely developed, delivered to the launch facility. It's one of my biggest regrets in my career because I spent 7 years working on it. And then it couldn't fly because there was the shuttle accident. It was not flying on the shuttle. It was flying with a Delta rocket, but NASA went into a paranoia, and they didn't want to fly anything for years. And then because we were secondary payload, the opportunity with a secondary payload with a global positioning system as primary was lost. It couldn't fly, period. So all the effort for nothing. But this was the first bare tether electrodynamic system. Then our colleague that many of you know, Joe Carroll, who has a small startup in California, he flew the TEPSI mission, quite interesting, 1 kilometer in length. Is electrodynamic. It's a CubeSat, but he managed to make it re-enter in 2 months, while otherwise would have been in orbit for a number of years. The very last one is this drag racer from our colleague Bob Hoyt, who also has a startup in the US. It's not really an electrodynamic system. It's more of a neutral drag cell, but I will not go into the detail. Coming back, because I want to really point out what, in my opinion, were the breakthrough and the breakthrough that led to technology improvement in the tether satellites. As you know, in the TSS-1R scheme, the anode is a big satellite, big sphere, let's say. In the case of TSS-1 was 1.6 meter in diameter, which is conductive. The cable is all insulated, so all the collection of electrons is done up here. And then it goes down here, the electronic current goes down here, and the cathode emits the electrons. And with this scheme, of which our esteemed colleague, Professor San Martin, is really the master of these things, you collect according to what is called the Parker-Murphy law, which is indicated here. But one major breakthrough came exactly from this school and UPM, and it was by San Martin, Martinez Sanchez Ajedo, Martinez Sanchez at MIT, and it was a famous paper in 1993, in which instead of using the large sphere as anode, they proposed to use the bare tether. And this simplifies the system a lot. First of all, you're getting rid of the insulation, but as we've seen, created more problem than anything else. You get rid of a large sphere, but if you respect this dimensional law of having a radius smaller than the Debye length and the electron gyro radius, and the first one is really the more critical one, because the Debye length is a few centimeters in the lower ionosphere. You respect those rules, then you collect electrons in the orbital motion limited regime, which is a lot more efficient than the other one. And I'll show you some results. The other breakthrough, in my opinion, so we went from large collecting spheres to bare tethers. At the beginning, everybody was thinking of bare cylindrical tether, like you see the one here from ProSEDS. But then it was proposed, and again, the first indication I found it in this paper in 1999 by, again, San Martin and Estes, one of my colleagues in the US, where I worked 15 years ago. In physics of plasmas, they proposed to use a tape, so a bare tape. And this is more efficient mass-wise. Actually, for the same mass, you can get a much bigger collection area, so you collect more electrons. And then we found out that this was actually done in Padua, that they are a lot better at surviving the macrometeoroids impact, because if you hit a tether like this, the tether craterizes, so the crater is typically 3 times bigger than the impactor. But if you hit something which is very thin, it's like doing a Gruyère's cheese. The size of the hole is almost exactly like the size of the impactor. So small impact creates tiny holes, but they don't damage, they don't cut the tape. And this was all done actually in the hypervelocity impact facility in Padua. But coming back to the OML, we have seen the theory, but actually our colleague in the US, Professor Gilchrist in University of Michigan, he did some very nice plasma chamber test, and he found out that the equation I showed you before, which is right here, it matches very well the data that was collected from the plasma chamber in samples of 0.5 meter or 1 meter. I don't remember exactly how long they were. And it does both for cylinder and tapes. And this was done up to 500 volt bias voltage, so it covers a large area, a large range, let's say, not area. So we feel confident about the orbital motion limited regime. If we go back to the TSS-1, and particularly to the TSS-1R, you see it was a massive system. This is the pallet that goes on board the space shuttle. This is the deployer. The terrible bolt was down there. This is a canister that deploys this 10 meters long boom to bring the satellite away from the tail, practically, of the space shuttle. And then the satellite is deployed from up there. And what I want to point you to are really the results, because this again from a paper by our Italian colleague in Rome from the Institute of Interplanetary Space Physics. Now it's changed name, but at that time was called that way. These dots are the experimental results from the TSS-1R collected during deployment, so before the satellite was lost. This goes up to 1 kilovolt, but the data actually covers a larger area. And you can see that the fitting, the fitting curve, this one, fits as about the same shape of a Parker-Murphy law, but it's much higher. It's 3 times higher. And so actually, the Parker-Murphy fits the trend, but not the intensity. The data system, even with a large sphere, is better than what we thought theoretically. And the OML is even better than this. So I think in that sense, we are on the right track. Now let's come to another important paper. This is by Jesús and colleagues. So this, a number of you are here. And this is a very beautiful paper, not because I'm there. This is a very beautiful paper, because it was really a refined analysis that Jesús did. And he found out, finally, what was this instability that we were in electrodynamic tether, the dynamic instability of electrodynamic tether that we were seeing in our simulation. And so he found the root cause of it. And the root cause was indeed something that we didn't suspect. Is the radial component of a magnetic field that generates some lateral forces that produce this H-shaped trajectory. If you look at the tether from the top, they start going like this. So it's in-plane, out-of-plane coupling. And Jesús found out that the real periodic solution, which are represented here, and that depends on the ratio between gravity gradient torque and the Lorentz torque. But these periodic solutions are all unstable. So long as you are on the periodic solution, the energy produced over one closed cycle is zero. But as soon as the periodic solution is perturbed, it grows. Did I represent correctly? So that was really important because we found out where the instability came from. And then another, this again from that paper is a figure that I really like. This is the potential energy. So the stable system will, this is out of plane, in-plane angle. Stable system will oscillate inside the air. But if the energy goes over the saddle point, which are here, then it becomes unstable. So from a stable libration, that is with this 8, which are increasing, eventually goes into a rotation. So the bottom line is that we have to dissipate energy somehow. Here you see the plot of the total energy versus the number of orbits. You see it's a slow instability, it's not a fast instability. But over many days, it builds up. And it's a little tricky because here it's all flat. And then at one point, bing, it goes out exponentially. So it's kind of dangerous. It doesn't give you much warning of what's going to happen. And another paper, and this is also very nice analysis, in which it was studied how to control this instability. Here is this, again, the H-shaped trajectory. This done with a nonlinear analysis. And you see that eventually you put the system on a periodic solution, which is, let's say, the least unstable, almost stable. But then eventually, small perturbation, even numerical perturbation, it takes off and it goes unstable. But we developed actually we used some technique that were used to stabilize chaotic system. And this is called the time-delayed autosynchronization. And then there is also the extended time-delay autosynchronization. We use that type of control logic to generate forces to keep the system on a stable periodic solution. And here you see the results after 15 orbit, after 20 orbit. So this again is another important contribution, because either you stabilize the system by using this technique, or the other option is to dissipate energy passively somewhere. This is also one paper in which some of us have contributed, again with Jesús and Juan, Martinez Sanchez. This was the guy at NASA that was funding us. He was a brave man. Because NASA is quite conservative, it's not super open to new things. But he was a brave man, he loved tethers, and so he funded us. And we developed a system to maintain the orbital altitude of a space station by using an electrodynamic tape. This was 10 kilometers long. The physics requires that for a boosting system you have to deploy downward, because the power supply where the cathode is up here, and with the power supply you have to bias the system to overcome the EMF produced by the motional electric field. But with only 200 kilograms of tape and taking out 10 kilowatt of power from the space station. The space station is 120 kilowatt to the load. We could generate a thrust up to 0.8 Newton and practically overcome, not completely, but to a great extent, the neutral drag of a space station. Why is this important? The space station requires about 8 tons of hydrazine per year. So about 80 tons over 10 years. And this is delivered by continuous, every few months, continuous delivery of hydrazine, which was supplied by the European, by the Russian, mostly by the Russian in the past. And using our system, which of course could not be left there 100% of the time, because the lower part of the space station is where all the cargo coming from Earth dock. So periodically you had to pull it out to let the cargo dock, the cargo vehicle. So we studied a case of 50% duty cycle and a case of 80% duty cycle, and we could reduce over 10 years lifetime the propellant consumption from 78 tons to 66 tons. Now, next week, there will be one paper, which will be presented by Alice in a conference in Baku, which also Gonzalo Sanchez is a co-author, to improve on this system. And with the latest, with what we know now about tape tethers and also some option of using a different technique for maintaining the altitude. So this one also is generating new thinking. Now, what we are primarily concentrating on nowadays in the European project that we have in cooperation with UC3M and other group that I'll show later is the deorbiting of satellites. So using a sort of light electrodynamic system, bare tape, to deorbit satellites. Here you see an analysis done on several of the constellations. Starlink from SpaceX, Astrom, Earthcare. The Starlink, this analysis was done a couple of years ago. It was the original configuration at higher altitude. Now the Starlink is flying at lower altitude, exactly for reason of reducing the lifetime in space. But practically everything that is above 600 kilometers of altitude violates even the older rule of 25 years maximum in LEO orbit. Nowadays it's reduced to 5 years from some agency, some important agencies. While if you use the electrodynamic system, you can re-enter various class of constellation in number of 2 months, 3 months, 1 year, and a year in this case, which is a heavier satellite, let's say 1 year and a half, roughly. So it looks very promising to use this electrodynamic system for the orbiting. Another important fancy thing we work on, and here there is also Claudio in the group, we put our mind under the guidance of one to using electrodynamic system in Jupiter. And Jupiter is a very interesting case because the magnetic field is very strong. The planets rotate very fast. I forgot exactly, it's 9 or 10 hours rotational period, so it's a big thing, but rotates fast. And for that reason, the Jupiter stationary orbit is low. Is at 2.2 Jupiter radii. And that means that the magnetic field here and the ionosphere, which is present in Jupiter, even at high altitude, is weaker than the Earth, but it goes to high altitude, rotates faster than the orbital system. And that means that without inverting the bias, or without using power supply, you can produce thrust and power at the same time, all at the expenses of the rotation of the magnetosphere of Jupiter. So it was very interesting. And we did an article on Scientific American, which actually appeared on the front cover of Scientific American, in which San Martin and I worked for months, and it was quite an experience dealing with a journalist of Scientific American. So especially for one was a difficult impact because they didn't reason like in terms of equation, in terms of general principle. No. They wanted the journalistic impact, the outreach. So it was quite an experience. But the idea was to capture an electrodynamic system, in this case it's a massive thing rotating, into Jupiter orbit, so closing the orbit, with the axis lower the stationary Jupiter orbit, and then slow down the system by lowering the apoaxis, visiting the various moons, and we could do a lot of flyby on moons. And then, if we wanted to liberate ourselves from Jupiter gravity, we'd use that technique I was telling you before of using the thrust above Jupiter's stationary orbit at apoaxis, and little by little increase the periapsis at altitude at each pass until the orbit was made open. I mean, it's a fanciful thing, but this is very, very interesting to work on. Now, what I'm saying, the story continues because we are working on, we have concluded one European project, and we are working on the second one, the ETPAC-F, together with Carlos Tercero di Madrid. This is the team of the first European project, the Fraunhofer in Dresden, us in Padua, the Technical University of Dresden, with Martin Tagmar, CENER, and Advanced Thermal Devices here again in Madrid. And now in the new project also the rocket factory Augsburg, which is the first customer of the system, joined. And this one consists of eventually of a system that will electrodynamic bare tape that will be attached to satellite at the end of life to make them re-enter. But we have already built with all the partners the prototype, and this is for a demonstration flight. So it's a 12-unit CubeSat. This one down here is the deployer, where we are very focused in Padua. We are mechanical people. And the upper part here is the cathode. This one use a halo cathode that consume a little bit of krypton. And the system is 500 meters long. The tape is 500 meters long. It is a tape which is not that easy to deploy, also because we wanted to make the deployer very compact. But it's been very interesting to work on this project. And with a new European project, this is a prototype. We had to build the qualification model, which is actually presently under construction, test the qualification model, and we are shooting for a demonstration flight with one of the rockets of RFA, of the Rocket Factory Augsburg, in 2025. So hopefully we'll see it fly. Oh yeah, this is a little video from CENER. It's more for public outreach, but we use it a lot every time we have any science fair of event open to the public, just to make them understand how the system works. Eventually will burn in the atmosphere. Of course, an electrodynamic system is suitable for satellites which are below 1 ton, because they have to burn in the lower atmosphere. We cannot do a control re-entry. It's a low thrust system. It goes stuck. Yeah, this is what I was telling you. We are shooting for a demonstration flight in 2025, and the coordinator is Gonzalo Sanchez Arriaga, and he's been the coordinator for both, for ETPAC and for ETPAC-F. This is my favorite one. We were a lot younger. This is Claudio, Jesús, and myself, And we were at a conference in Puerto Rico, and we visited the Arecibo radio telescope. And this is under the focusing spot. Arecibo telescope is gigantic, it's a paraboloid, and the paraboloid then focuses the radio waves into this dome. And we were presenting our tether paper, of course, in Ponce, in Puerto Rico. But I want to finish my presentation with these very few words. Dear Jesús, it was a great honor and pleasure for me to collaborate over many years with a brilliant scientist and a friend like you. Thank you. Bunch of references, and this is a rendering of ET-PAC. Oh, do you have any questions? Yeah, sorry, I burned my time, I think. Yes, yeah, I will. Both of you. Was try to find out. It was 2003. We were in Ponce. Either 2001, 2003. Yeah.
That is not longer there.
Well, after Enrico has reminded us about the history of tethers, adding a part of history, recent years I was not familiar with, we are going back to early years, so the years in which I was involved with Jesús in tether. So this is a very well-known picture, it's available everywhere on internet. It was centered on the process, which is working. And it had a lot of proposed things, of which I think that a few, for example, the yes that I have, the yes to that is there has been added. The involvement of Jesús was basically with the SEDS flights and with something that disappeared from here. And I was astonished at how things work in the United States. So many years of working on that project, it was cancelled and it disappeared. Later, after Enrico published the Handbook of Tethers, no mention. It was gone. Probably it was painful because of all that. So those are the programs. These are the grants and projects that are related. Basically, these are San Martin grants. Yeah? At some time, there are coordinated grants where San Martin with the head and the part working on plasmas and electrodynamics, and Jesús will lead another team working on the dynamics. Yeah? At the same time, Enrico had a set of grants with NASA, more related with the system, with the project, concrete projects. The ones we were doing were more theoretically. So of these projects and works, I mentioned a few. Some of the work with by Jesús related to the process, the propulsive set, small expensable deploying system. There were some seminal papers on the dynamics on which Jesús did some interesting findings. One of them is the phase map of the deployment, finding some stable positions that could be located for the deployment. Here, it's not painted here, but there are some areas that have to be avoided where the tether goes slack, tension goes to zero, and they have to be avoided. Another interesting development in the dynamics of the deployment is that even if there is stable deployment direction, if you're interested in getting a local vertical aligned tether, there is an interesting point here in which you can regulate and get one exact position in which it goes there without libration, just with the radial speed. If you stop here, you get what you need. This is interesting in systems like prosets with an inert end mass. It's not so important in systems with like the TSS, which is a satellite within its own OCS system that can control the oscillations. With an inert system, there is no possible way to control the libration. So you really need to get it right the first time. This is what this development by Jesús really gets. I was not yet involved in that place, but I did use all this work in what I was doing later with Jesús, concretely my PhD thesis. So this is, don't look at the guy, which Enrico has mentioned before, as an interested person in this field. Just look at the deployment system. This is the canister with the tether is stored. It goes out this way, and this is the deployment control system. It used to be called the barber pole system. It's just a rod along which the tether is rolled. There is a perforation here. The tether goes through it, so that if you rotate the rod, the number of turns that the tether goes around increases. Therefore, you can control the tension of the tether. Here you have simply control the rotations of this barber pole, so to call it, and then you get the simply the only control variable is tension, and the only input you have is the rotations of the. So this makes the deployment a very difficult thing. I remember at this time visiting Enrico in Boston, and I could hear from his pulling his hair in a in a figurative way. He still has all of it. I cannot control it. So difficult to control it. Huh? So this is an important work, because Lorenzini and Jesús found some areas where the deployment was not sensitive to the initial tension. Some of the parameters of the system that would be very difficult to determine. So you get some areas of insensitivity that would guarantee, never completely, but it would guarantee a better output. The main project I was involved with, Jesus, was the the SET-SAT, in which SET has a double meaning. There was a students' association, students for education and development of space, or something like that, which nicely met the small expendable and deploying system. So the whole idea is that this was a student-built satellite. It needed, obviously, a cheap launch, a secondary payload. So one of the ways to get the required orbit, when you can only get a lower one, is to use a tether as a slingshot release system. So there were several iterations. One of them had the deployments, what you saw before, this deployment system, plus the satellite, student satellite, release from the shuttle, not along the vertical. You will release a certain angle so that the satellite and the tether will vibrate about the shuttle. At a certain point, you cut the shuttle here, and if you don't do anything else, the satellite will follow this orbit. Very nice, you get a high perigee, but the apogee, but the perigee is low, so that drag will be important. So one of the ways to improve the lifetime of the satellite is to use the mass of the tether to get an additional boost. So that instead of cutting here and letting the satellite go, you cut down, and it's the whole system that goes. This means that the center of mass orbit is a little bit lower, but you can get a second opportunity if you get the phase right to cut here at the time in which the tether is vibrating in the appropriate direction, so that the satellite goes on its own and the tether is cut and re-enters. So this cut gives an additional boost, and this ensures that the perigee is higher. So this improves the lifetime of the satellite. So you get this is very sensitive to the timing of the libration and the orbit. So you have to ensure that the second cut is done at the proper time. It would be ideal that it should be right on the apogee and on the right direction, but you are never going to get the coincidence of these two frequencies. So there is a set of values in which you can get the optimum. Is not reached in the first orbit, but in the second. If you would wait more time, you could get it exactly aligned with the vertical and get the optimum, but you cannot wait forever. So this would give an additional boost and increase at this time with the conditions we were using and average solar cycle and things like that. We will get nearly to 3-year lifetime from this orbit. This had one problem, and this is another of the fields where Jesus did a significant contribution, is the idea that the end of the tether is left free. Now, in other flights, like the TSS-1, you had one satellite in one end and the shuttle in the other one, and you can keep the tension. The moment you get one end free, and this is a very light tether, so you have here a whiplash condition. As with the effecto látigo is the whiplash condition, in which you can get a concentration of energy at the tip. So the stability of this motion was important. Jesus did a very complex, I still look at the equations and I get astonished, in which the deviations of the tether from the straight line are computed. The equations reduced to a set of Sturm-Liouville problem, so that you can get the eigenvalues and the shape of the functions. And it doesn't match anything, but with an expansion, with a perturbation method, you can get the shapes, the natural shapes, they closely match the Lagrangian functions. Not at the first, but if you get an expansion, you are getting, with additional terms, you are getting them. With this, you can compute the evolution of the different modes. They were all unstable. They were unstable because this doesn't have any dissipation. But still, you could see that you have a leeway, at least of up to 4 orbits until the most unstable term shoots up. So the idea is, well, it's unstable, but you have a leeway to perform the injection before this gets unstable. Actually, we only needed an orbit and a half. This still was a little bit worrying, and there was a possibility to improve it instead of leaving just the tether. Well, I forgot to say something that is important, and is that there were, Enrico had developed perhaps the best simulator for a tether. And all these simulators would have dashpots or masses, but it's very difficult to, because you end necessarily in a mass, to model this free end. That's why this theoretical work was important. Now, you remember what is here. You see that there is the possibility, instead of cutting here and letting, perhaps you can cut here and let the whole thing go. The advantage of this approach is that if you put a mass here, then the tension never goes to 0. These eigenvalues that have free going, that is a whiplash effect, these eigenfunctions become very common, normal, vibrating rope. And this stabilizes. It reduces a bit the effectiveness because the center of mass is lower. So you don't get as high, but you can get, depending on the masses, you can get, if you get the optimal position, you can win over 1 year. We were getting close to 3 with this in the same atmospheric conditions. We will get that to 3 years, and you solve the instability problem. That was another work. Another project in which Jesus was involved is deploying not from a circular orbit, but from an elliptic orbit, in which you get more uncertainties. So one of the results was to detect some areas where the deployment was not sensitive to eccentricity and to the other parameter against that, which anomaly you started. These are not exact intersections. If you look closer, there is an area, but then it gives you another area where the deployment can be made insensitive. That was another interesting. Now, regarding the process and the bare tether proposal, there were other papers here, but I have chosen those in which Jesus was involved. There was one with VAS. Now, the difference between what is that the TSS-1 system, we have a conductive satellite. All this surface collects electrons, and the tether is insulated. It only carries the current. Now, the concept of bare tether, you don't need a mass at the end. You don't need a collector. It's the tether itself that is in contact with the ionosphere and collects. You only need here a hollow cathode that is ejecting an electron gun that returns the electrons to the ionosphere so that it closes the... So it gives much more flexibility at the expense of similar instability to what we saw just a moment before. So Enrico has already mentioned some of those results. The project process would have a conductive part that should be aluminum, and then an inert part just to keep it balanced, so that you don't have, again, this whiplash. So it will be 2 sections. Jesus worked with a 2-bar model, and as Enrico mentioned, he found the instability related to libration, in which going this way is much easier than going all the way, just because of the structure of the energy. And he found also the solutions, the periodic solutions for the tether, and the dependence with the inclination of the orbit, and this parameter epsilon, which is the rate within the electrodynamic torque and the gravity gradient torque. You mentioned the force, but it's the same radius, so it's obviously the same. So these are unstable solutions, but well, halo orbits are also unstable, so the presence is important. There is another development of things is that there were many studies about tethers in a circular equatorial orbit and with aligned dipole. Very nice, but the moment you realize that the dipole is inclined, this component produces a destabilization effect. Well, this is nearly the end, and it ends in a very sad way, the disaster. What happened? Well, the failures of the two TSS flights produce a sort of alarm, because the moment it's cut, there is the danger of recontact. That the satellite and tether, and the hanging tether, 30-kilometer tether, in the next orbit will cut and hit. So this left NASA people, well, they were so nervous, going a little bit back here, that during the SETSAT deployment, the proposed thing is that the shuttle would rotate its attitude to keep always normal, so that it will not tangle, and there was a big problem, fear for the safety of the. At times I felt a little bit, we have been working so much in seeing that this is unstable, we would have killed the whole thing. There was a problem that I raised, because I read that Professor Shears was going to be here, so I did what is the not invented here fear. But I think that the main problem was the fear for severe being broken, or even debris cutting the tether and the portion that would hit. So there was a very early and very alarming paper by an engineer at the same center, in which the predictions were, even if he can recognize that the probability, in the worst case, he was studying if it's cut here, different heights, different moments, different sections. The worst case was a probability of 1 in 10,000. But he started talking about the avoidance maneuvers, and everybody got scared. There was a later paper in which it's not so serious and no problem, but the damage was already done because of the guys at Marshall that were nervous. So at the end, the project was cancelled, which produced, Enrico was so mad that completely hit every word, but there were many years of this work. And the students that were behind SET explained later what happened, and basically was fear for possible damage, so they kept it. And as Enrico also mentioned, project was later cancelled, not only because of that, but the accident of the shuttle, the flight that was proposed was delayed, then the solar year was advancing, and plasma density would not be enough, so it was finally, because of different and also fear, it was cancelled. So this would end in a sad, we were all frustrated, but there is, I'll go back to the first, there is life after that. First, because of the things that Enrico has mentioned that I was not aware, and also because of some other things of these proposals. I think not only San Martin, Jesus has also worked on these things. There are also some projects that at the height of the tether years, there were some proposals. For example, Longuski was working on many projects for Mars, aerobraking in Mars missions, in which you would deploy a tether in the Mars atmosphere with a balloon, and it will save a lot of fuel just for the capture. These things now would be interesting. And now I had mentioned here the YES-2 satellite. Here there will be the YES-1, because it has something to do. At some time, we received in Madrid a visit of a couple of Dutch students from Delft. They were enthusiastic, they were coming, and they were coming but I think that we're all a little bit now, and not much attention was lent to their proposal. But they did launch a tether, was the young engineer satellite, which was supposed to deploy a sub-satellite for re-entry. But I think the plan was not well thought because they were using a high orbit, a GTO orbit. And deploying a tether in GTO orbit, that's very dangerous. So the satellite went, but the tether was cancelled. Later on, in 2007, they launched a less ambitious mission, but this one deployed. But they were only allowed to deploy when it was already about to re-enter, a very low orbit. So it was a satellite that would deploy a small sub-satellite, a balloon, an orange balloon, and when it was already very low, it started the deployment so that it will re-entry, and they kept telemetry only up to the moment that the thing was released. The sub-satellite was headed, the latest data, was headed towards Kazakhstan. So if you have time and go in summer, Kazakhstan is huge, 4 times Spain. So look in the mountains and lakes, and perhaps you find an orange balloon, and you can get the rest of the story. And this continues, but I have reached up to the moment I was working on this. So thank you, Jesus, because of all this, and thank you for your attention. Thank you. And now, sorry, I have a class. I have to rush to it. ¿Cuánto me darán por esto en el rastro?
So, thank you, Manuel, for organizing this deserved and long time waited homage to Jesus. I am very proud to be here presenting some research. We met, I don't know exactly when. Jesus, you remember, in Monterrey, Clearwater, I don't know exactly. But then we met many times in different meetings, fundamentally from the American Astronautical Society. So in Sedona in 2007, also in a Spanish meeting. No, you can know that it is a Spanish meeting because of the smiles and probably the wine, right? And then in the Que Pasa series, this was one in Stek in Norwich. You see everybody looking to the camera, and we discussing. I don't know exactly, we were discussing, but with a high probability he was protesting. You see, Martin, the stick was too much cooked, and I say, yes, of course, and there is little amount of French fries or things like that, but also we did some research, right? Not only the joy of the meetings. And here, I think is our first joint paper when Jesus was working in the stability of the electrodynamic tethers. Later, I joined the group in this important project. The Jesus research captured the attention of the ESA and granted him with an important project. I think that the results are not still completely exploded, but they are there, and probably many papers will emerge from there. At these times, we realized that there was a strong analogy between the dynamics of the tethers in fast rotation and the dynamics of a normal satellite, of a mass point satellite perturbed by the oblateness of the Earth, and we explored some results. But today I am focusing principally in the dynamics about the collinear points. This paper was a splinter of the report of the ESA report, and we investigated there a particular configuration of the dynamics that Jesus formulated, what is called the fridge for fast rotating inert tether satellite around the z-axis. And the z-axis means, for instance, for an orbit about an oblate body, the perpendicular to the equator, but in the restricted three-body dynamics problem model, the direction perpendicular to the orbit of the primaries, right? So we approached the problem by computations on families of periodic orbits, studying the stability, seeing how the shape of the orbit of the center of mass changes, the stability characteristic change also, and so on. So today I am trying to complement this information we obtaining with periodic orbits with an approximate analytical solution, right? So first recall basic things about the liberation point dynamics, then the model, the Pelaez fridge, how to approach this model to obtain an analytical solution, and then discuss the dynamics to compare with the results previously observed by the direct computations of periodic orbits. So the model is typical for the dynamics about natural planetary satellites. We have a big mass, the planet, a small mass, the satellite, and some body that is orbiting close. So for these dynamics of the restricted three-body problem, we can make additional simplifications. First, the distance to the orbit it will be always very small compared with the distance to the planet, and then this mass is much heavier than this other mass. So under these amplifications, we arrive to the Hill problem model. And the Hill problem model is Hamiltonian. You all know what a Hamiltonian is, basically a state function from which we can derive the dynamics in a very simple way. If you have a problem that is Hamiltonian, normally you are very happy because you can deal with scalar functions rather than dealing directly with the flow. So in the Hill problem model, we have the conjugate momenta to the coordinates, and also we have two physical parameters. The rotation rate of the system is formulated in a rotating frame, and also the ratio of the mass of the smaller primary to the total mass of the system, but they are dispensable because you can choose units, and in these units you make the parameters to be one. So it's a very nice model because it's a very simple model and has wide application because it does not depend on parameters, right? So it's very simple. For this model, what is of interest for us here is that it accepts the collinear points that lie in this rotating x-axis and maintain in Hill units a constant distance that take this value. You can move to a particular system, you just scale the dimensions of the system, and you obtain the direction. And these liberation points are of the saddle times center type, so they are unstable, but we know that there are, in the linearization of the problem, vertical infinitesimal oscillations that are periodic orbits, and also small oscillations in the xy plane. This is in the linearization, but these orbits can be continued to the full model because they conform families of periodic orbits, and eventually, from the planar Lyapunov orbit, we obtain a bifurcation to the three-dimensional space, which are the classical halo orbits, right? So, but this is for the Hill problem model that is very well studied and discussed in the literature, but we have additional terms here because, okay, yes, we need to add the tether, right? So even in the classical, to make the problem handleable, the tether is normally modeling like by a rigid rod connecting the two end masses. But we have moved from a 3 degrees of freedom problem to a 6 degrees of freedom problem, right? But we can make additional assumptions, and then in the case in which the tether is rotating fast compared with the rotation rate of the primary, we can apply the usual averaging assumptions. And if in addition we use the Pelaez-Fritsch configuration, that is that the tether is rotating continuously parallel to, in a plane parallel to the plane of the primaries, we can make additional assumptions, neglecting terms of disorder. The physical length of the tether will be normally very small compared with the distance to the primaries, so we can neglect and make expansions, neglect some terms, and at the end, Jesús arrived to this simple, very simple model, that is the Hill problem. Dynamics perturbed by some term which is proportional to a physical parameter. Now we have a physical parameter related to the physical length of the tether. He had the ability of concentrating all the physical parameters of the problem into this single one. So the physical length, the distance to the primaries, the mass rate, and some relation between the end mass tether. So we have a Hill problem perturbed by some term. And then this does not affect the existence of the equilibria, but this modifies the distance of the equilibria of the Hill problem, which now depend in an implicit form, but depend on this characteristic length of the tether, right? So we can make this implicit function explicit in terms of this if we want to obtain the distance expanding and so on. And, but at this term which is exactly formally the same as the perturbation due to an oblate planet. So when we realized that, we were very happy because there are a wealth of results related to the previous problem that we need only to apply to this new one. So some formulas here. I was ashamed once, I don't know if Juan Luis remember, in a seminar of the Politecnico of the Milano, because the students were preparing their presentation for some meeting, and they invited me to a seat. I say, okay, well, I'll be there. And then I remember one student presenting, and Juan Luis saying, no. Formulas are not interesting for nobody. Formulas are in the paper. You should not do that. I was in my seat making it smaller because I normally present the formulas. But anyway, I learned later that Jesús was known in Harvard like Don Quixote of the formulas, so no problem with some formulas, right, Jesús? They are okay. So this is our problem, that is the Hill-Oblate problem, that is arranged like a perturbation problem in which we have an integrable part and some perturbation which is nonlinear, is integrable. And then what we do first is to find the integrals of the integrable part and then try to extend to the whole problem. So in this way, in some region of phase space, we have a non-integrable problem that has become integrable in some region for our interest. And this is exactly what we do. The procedure is standard. First, the non-integrable part is made only of quadratic terms that stem linear dynamics with constant coefficients, so the integration is trivial. For our purposes, we first make a canonical transformation, a linear transformation, in fact, that decomposes the integrable part in 3 different parts. This is a hyperbolic term, and these are harmonic components of the problem, right? But these are the 3 integrals that make the zero-order term completely integrable. And the problem can be approached then trying to extend these integrals to the perturbations. But since we are interested in particular on the orbits emerging, the one-to-one resonant orbits emerging of the dynamics, what is better to do is, after realizing that these numbers, the frequency of the 2 oscillators, are close enough, then we write one of them like the other and some small term that we move to the perturbation. In this way, we chained these 2 elliptic oscillations, these 2 harmonic oscillations into a single elliptic oscillators, and then with perturbations we can study the resonant dynamics. So, when we have doing that, we have here one integral related to the hyperbolic part and the other integral related to the synchronized elliptic oscillations. And what we do by perturbation is to extend these integrals to the whole perturb problem, to the Fritz problem. Then we have an analytical solution from which we can start the dynamics, right? So this is what we do. And then once we have done that, we are normally, I don't know if there is space missions related with the hyperbolic dynamics, maybe to abandon the solar system or things like that, I don't know. But normally, we are only interested in the slow components of the dynamics to design useful missions. So in these dynamics, once we obtain the reduced problem after truncation to some order of the perturbation approach, we know from mathematicians that the phase space, the reduced phase space, is of 1 degree of freedom, but it is not a plane, it is not a cylinder, it is the sphere. So for dealing with the problem, with the reduced problem, it's typical to use the Hopf variables in the sphere. No? They have some relation with the Cartesian coordinates of the problem, and in these dynamics, given for some value of the energy or the Hamiltonian value, we then only identify closed curves and fixed points of the elliptic and the hyperbolic type. And in these reduced dynamics, the fixed points correspond to the periodic orbits. So here, this fixed point corresponds to the vertical Lyapunov orbit, the other to the planar, and this other to the Hello orbits. It's now from the dynamics of the Hill problem, and it happens also in the modification. So we can have our analytical solution here as many terms as we can, as our computed or our memory can handle. But for describing qualitatively these dynamics, we only need, in this particular case, to retain this short Hamiltonian, in which L is the dimensions of the elliptic oscillation, is a dynamical parameter. The K's are related to the other parameter, the physical, the characteristic length of the tether. So we have a problem depending on 2 parameters, and the I1, I3, I2 are the coordinates on the sphere, right? So deriving the differential system from this Hamiltonian is very simple, and in fact, from these equations, it's very simple to be here I1, I3 vanish, then this vanish, then this vanish, then this vanish are equilibrium position. It's very simple. So we have that for any value of the parameters, we always have this kind of equilibrium position that in the sphere that correspond to the periodic orbits. On the other hand, if I3, for instance, vanish, this vanish, but this don't. But there is another relation here that allows us to explain the condition for I1, for this term to vanish, then the value of I1 depends on the parameters of the system, and so on. So we have the typical equilibria corresponding to the Lyapunov orbits, corresponding to the Halo orbits, and also, like in the non-perturbed problem, like in the Hill problem, big orbits that connect the planar and vertical Lyapunov orbits by means of, they call, a bridge of periodic orbits. So the following thing, once we have identified the equilibrium, is determine the dynamics in the parameters plane. So we say that the Lyapunov orbit exists always, but it is not the case of the Elo or the other orbits, because we have here a square root, and to exist the equilibrium, we need to fulfill some condition making this a positive quantity. Right? Discussing these terms that take some value relating the dynamical and the physical parameters provides us the conditions that we need to exist this value. And in particular is this value, the value of the energy of the elliptic oscillator needs to be higher than this to have here real values. In the limit, when both are the same, means that these orbits, this equilibrium, start to appear. They do not exist, and in the limit start to appear. So for given values of the two parameters, we have a point, we have a relation between the two parameters which determine a line in the parameter plane in which the dynamics changes. So this is represented here. These are the bifurcation lines that we computed in our model, and we have different regions in the bifurcation plane determined by the liberation point distance, which means the characteristic tether length, and also the size of the orbits. And in these regions, we have different number of the equilibrium. In the classical Hill problem, we don't have a parameter plane. We only have a parameter line because it does not depend on parameters related to the energy of the problem. So we see here that changing from the Lyapunov, this region with HELO, and this region with very high orbits, with other kind of orbits, changes may change notably to find a point for certain tethers characteristic length in which the whole dynamics explode, appears. So in the classical Hill problem, we can have here L orbits, but with some size, starting with some size. And if we want then incline it, the size is larger. But with a tether, we can move here. And then we start directly with a halo orbit that may be very small. Maybe it is interest, I don't know, for mission design purposes. So it is an important difference. So when we have investigated the different regions in the phases, in the parameters plane, we can discuss our problem depending on the tether's characteristic length and the energy above the liberation point orbits. So we can do things these days are very simple because we have a lot of technology. So we have a Hamiltonian, well, I mean, except the dirty ticket machines in the metal tube. But normally the things, you have a lot of tools to make our computations. So we have here a simple Hamiltonian. I select the parameter planes and regions, so I am fixed this value, I am fixed all these coefficients, and I can represent for given values of the energy by means of simple contour plots that your computer, your programs for sure have functions to directly evaluate to understand the dynamics. So, for instance, in this region, or in this region in which the dynamics is more or less the same, we can create contour plots of this Hamiltonian. These are opposite views, the x-axis, the minus x-axis, and then with these contour plots, the different colors are used to enhance changes, are not related to the same values of the energy, right? But to enhance changes, to learn the dynamics, we see here a fixed point of the elliptic time and some circulation around it, a fixed point of the elliptic time, some circulation around it, and then circulation motion about the elliptic points. But if we cross this line, or we cross this other line, then the bifurcation happens. The flow compresses here, the other remains most of the same, but then this point changes to hyperbolic character in the bifurcation process in which the halo orbits appear. Elliptic points, stable on the center manifold because we have removed the hyperbolic dynamics, and so on. So we have a very simple way to check what happens, and with Jesus we have observed by the computation of families of periodic orbits. So Jesus realized that all the parameters of this model, a fast rotating inert tether in the direction of the zx, can be compressed into a single physical parameter related to the tether length. The tether length can then be used as a control parameter to change and to modify the dynamics. And this can be used to modify not only the shape of the liberation point orbits, but also its stability characteristics. So the analytical solution complements and confirms what we have observed numerically. It does not replace the numerical approach because we formulated the problem as an one-to-one elliptic oscillators, and we know that there are other periodic orbits that are not in the one-to-one relation, are 1 to 2 or 15 to 18 or something similar, right? It cannot replace that because we are constrained to the center manifold. We are not dealing with the hyperbolic instability, but it is there. We are in our plane avoiding it, but once we have something perturbed the model, the hyperbolic instability will have its effect. So both the approaches are complementary, and I was very happy to find that an analytical solution, very simple, qualitative, kind, describes the results of this important report. Is a report that the part of them we have published, and I consider that there is a lot of food there to continue publishing and investigating things. So thank you very much, Jesus. You always have been there. You know that for me it was important because I was never ashamed to take the phone and say, Jesus, I don't understand these simple things. Please explain me. And he always explaining me the things. He could tell me, Martin, study, this is in the books at very low levels. No. He has a vocation as a professor and has the ability of making us understand the things. So it was in a meeting. It was a Japanese meeting. We didn't know, right, that the uniformity was mandatory and to present and so on. So thank you, Jesus, very, very much for being there, and I hope you also continue being there for many, many years. Yeah. Well, to find, from the analytical point of view, you are constraining to a very particular dynamics. In our case, the one-to-one elliptic oscillator, so you cannot find more. If you want to find more analytically, you need to reformulate the integrable part, like, for instance, a 1-to-2 oscillator. Otherwise, you have the periodic orbit computations to blindly checking how the stability index is associated to the periodic orbs evolved and to find the bifurcation and so on. There is a wealth of work done related to this kind of technique by the Gerard Gomez and the group of Barcelona, not applying to the tethers, right, but applying to the normal Hill problem. So you can detect in this kind of Poincaré maps to study the dynamics of directly by the evolution of the stability indices to check how new families of periodic orbits evolve. So, thank you.
Es que no sé cómo apagarlo. No sé cómo apagarlo.
Hola, ¿se me oye? ¿Se me ve? Ok. Pero si alguien dice alguien, ¿yo voy a escuchar o no? Espera que comparto. Estoy compartiendo pantalla. A ver, si he visto a alguien. Se ve perfecto. Ok. Vale, pero yo no escucho nada. Así que voy a ciegas. Ok, vale. Bueno, si hay algún problema, me mandas un WhatsApp. Sí, trataré de tenerlo abierto. Ok, gracias. Vale, entonces, ¿empiezo yo? ¿Empiezas tú? ¿Quién va primero? Bueno, tú decides. Si quieres, voy yo. Ah, vale. No, no, entonces vamos con el programa. Faltaría más. Vale, vale. Ok. No te trates mucho. Ok. Dejo de compartir esto. De acuerdo. Trataré de ser breve. Ok. Esto y esto.
Yeah, it's ready. Yeah, it works. ¿Cómo? Más cerca. Vale. Okay. So, well, good morning. I'm going to talk a little bit about tethers and to close the, let's say, the track of tethers. Everything, I think, the important things have been already said. Can anyone can open there? No. Yeah, thanks. And then, so my point of view here is more, let's say, personal than scientific. And one disclaimer is that, despite being personal, I have no photos. So the photos are there in this or a similar one, but I don't know exactly where this thing is. No? Have no idea. So all my photos from before 2010 are now lost. So, and this is something for this seminar allow me to know that I don't have past before 2010. So again, no, my presentation is going to be quick. It's going to be I mean, the path that I follow during or before and during my PhD with Jesús. And the idea is to go through which is the problem that we wanted to solve, the context in which we started, the solution proposed by Jesús, and then the result that we get. No? Well, this is the paper that Enrico mentioned before, but for some reason is not correct. But this is a new kind of dynamic instability in electrodynamic tethers. The paper by Jesús and collaborators in 2000, and the idea that was previously described by Enrico is that this kind of instability was something to avoid, because in principle the operation of tether in space can be jeopardized by the fact that we have these electrodynamic forces pumping energy into the rotational motion of the tether, and at some point we can get something that is rotating or it is unstable. One point here is that no damping is considered in the analysis, but still it's something that, although damping can improve the behavior, still is something to be concerned of. In which context we started working or facing the problem? It was about year 2005. As was previously described, the mood of the tether, of the people working on tethers was this one. No? I think that this cat reflects perfectly the mood of the people working on that area, because of all the missions that were cancelled after shuttle disaster, etc. But despite this mood that was, let's say, sad, close to in the department of applied physics to aeronautics, there were a bunch of students, Jordi Fondecava, Yago Andrés, Gonzalo Sanchez, and myself, that were interested and were really willing to know more about tethers. And we started to collaborate with Jesús. And in my particular case, I started to work with Jesús in developing a simulator. It was a dumbbell model, so a rigid model. And at the same time, for instance, if I remember correctly, Jordi was working on a lumped masses simulator, and the solution that was proposed for the instability. I mean, Enrico before talked about how to control the instability using time delay options, but the idea of Jesús was to try to reduce or even cancel the effect by design. So using the design of the tether to reduce the instability during the mission. The idea was simple. The idea was to cancel the electrodynamic torque because we want to remove this energy pumping effect. So well, here, so the only, no, it's Juancho, only three equations. Here we have, which is the condition. So this parameter, in fact, was already introduced by Manuel Ruiz before. The idea is this is the parameter controlling this effect. So we want to keep it at as small as possible, or even zero, or even negative, no? To removing energy from the system. So this involves the computation, if you want, of the torque of the magnetic of the Lorentz forces. So we need a good models for the magnetic field and also for the current along the tether. So this is one of the things that we had to develop, if you want, for in the path to describe correctly or describe in a more precise manner the concept of the self-balanced electrodynamic tether. Sorry about this, because this is cut and paste, and for some reason, so this is for another paper, that is the asymptotic computation of the current along the tether, and the idea is, as I said before, no, the idea is to remove the instability by design. So for that, we need to have a good prediction of which is the mission, and an accurate prediction of electronic force and its distribution along the tether. So the development of this is the dumbbell, no? The simulator that was developed was the one allowing us to do the mission analysis, and then well, this paper that is not that doesn't appear here, but is the one that contributes to understand and compute in an efficient manner the current along the tether. And then, starting from the SVET concept, starting from the self-balance concept, well, here there is another paper talking about the energy of or which are the energy balance in the tether, and how can we which are the different methods that we can try in order to reduce the injection of energy in the rotational dynamics. But here, what we see is different concepts that derive from the self-balance concept, in which what we are trying is to describe a system that is from an engineering point of view, if you want. So using closed-loop control, we can, for instance, for the continuous SVET, what we want is to keep this parameter epsilon equal to 0 all the time. For that, we have to measure the electron density, also the intensity and the magnetic field, etc., in order to be able to know which is the position, or which is the right resistance that we have to use in order for the current profile to produce an epsilon that is equal to 0. And there are other options, but this is, let's say, the one in which we try to keep this value of epsilon equal to 0 all the time. The result that we got by the time, so we applied this concept of self-balance to mainly to two scenarios. Well, more than that, 3 I think, but I'm bringing here 2. One is the orbiting one. So we are considering the end of life deorbiting of a satellite. And here you see the comparison between an object that is, or a satellite that is not balanced with one that is self-balanced. So the idea is that the design of the tether system, in one case, doesn't take into account the importance of the mass distribution. So you have a big mass in top, if you want, and a small mass down. And then if you take into account the self-balance concept, you try to have something in which the mass is shared more or less equally between the two parts. And with that, what we can see simulating with dumbbells, so considering only rigid effects, so a rigid model, what we have is that at some point the not balanced tether of 5 kilometers starts to rotate. No? This is the in-plane angle. And this is how, at some point, it starts to rotate. In the same case, we can see how this instability takes place. So the out-of-plane angle is increasing till a point in which we almost arrive to 90 degrees, and at that point we have the out-of-plane, the in-plane instability coming in. No? Finally, which are the intensities that we get? So the mean intensities along the cable. Another thing that we did is compare the control strategy that we mentioned before. And here you can see the difference between having no control. So in this case, we have a self-balance. For some reason, we have a self-balance, but is without any control. So we see here on top that the instability, so the angle, the out-of-plane angle, is increasing when we are arriving to the low layers of the atmosphere. And in the other two cases, we start to control earlier, at 27 days or 40 days. In that case, the rotation of the angles, the in-plane and out-of-plane angles, are limited, the oscillation, but at the cost of having descent time that is larger. And finally here, comparing two different approaches for this extended self-balance concept, we have for the indirect, what we have is basically what I mentioned before. No? So we are only measuring the electron density, and we are estimating which is the value of the intensity of the current that we need, or the resistance load that we need in order to have the intensity, the current that we need. And this is the time spent in the deorbiting. So we start, in the x-axis, what we have is the initial rotational energy of the system. So if we have no rotational energy of the system initially, all the in any of the options finish, or the mission finish around 40 days. But if we start to have initial conditions that are not so good, let's say, what we have is that with the continuous SVED, we are able to finish the descent in a controlled manner, even with rotational energies that are high. In the case of the indirect, this is not the case when the initial condition is out of plane. Anyway, the idea is that we develop, let's say, a simulator for doing mission analysis and to test the concept, and also extend this concept using certain control laws that allow us to improve the performance if needed. The other scenario in which we introduce, or we consider, the SVED concept was in Jovian capture. As Enrico said before, this analysis in by the time were interesting because Jupiter was a really interesting celestial object from the point of view of exploring with tethers. And in fact, there was a previous study by San Martin and collaborators about how to capture how to perform a capture maneuver in Jupiter using a rotating tether. Here, what we said is, well, is it possible to use a non-rotating tether? So to use something like a self-balanced tether in order to perform the same capture maneuver. And here we have the results. On one side, we have a limit given by the maximum temperature that because the intensity that you have along the current that you have along the tether is high, so the temperature that you have is high as well. So you have a limit from the point of view of the temperature, and then here in black we have a lower level to perform a capture. So from here we can see the relation, or which are the needed length of the tether for different radius of the periapsis that we are targeting. So basically, during my main, main collaboration is the other way around. No? The main collaboration of Jesús with me was during my PhD, and there what we did and what I did was to try to understand better and to extend the concept of the self-balanced electrodynamic tether. And in that, Jesús contributed a lot to this better understanding of the tether dynamics, but also, at least with my PhD, with an engineering view. So trying to go from the dynamics to a system that can actually fly, and identifying these potential issues for tether emissions. And also, I mean, apart from doing the analysis, Jesús also came to the solution to overcome the issue with this concept, no? And also try to address or start to address the control problem. And the outcome of that is that I graduated more or less successfully, and that I have a certain background that allow me to collaborate humbly in the current initiative like the ETPAC that is led by Gonzalo Sanchez in UC3M, but we have many others in outside. So thank you, Jesús, because in the start of the path was also my start in this path, in this research path, was thanks to you, and I'm really grateful for that. And thank you all for listening. Probably there is no questions, so we can move to the next speaker, that is Elena Fantino. Can you?
Hello? Okay. I assume you can listen to me, and I will share my presentation. Okay, good morning. Hola, buenos días a todos. Buenos días, Jesús. Thanks to the organizers for this workshop and for giving me the opportunity to present today. I have chosen this topic, end-to-end trajectory concept for close exploration of Saturn's inner large moons, for two reasons. It's a recent work. It was published during the summer. I take this opportunity to thank my collaborators and co-authors, Burhani, Fernando Solano, Roberto Flores, Elisa Maria Alessi, and Manuel Sanjurjo. And this is the culmination of many years of work. And the other reason is that this work is deeply rooted in the collaboration and in previous works that I carried out with Jesus. So I thought it was a suitable topic for today's celebration and event. What we're talking about the exploration of the Saturn system, which takes us back to Cassini-Huygens and the important discoveries that it made that we are all aware of. I'm talking, for example, about the plumes detected emanating from the surface of Enceladus, but not only, many features regarding the inner moons of Saturn. And the idea that I want to illustrate today, and that is the subject of this work, is a proposal of a new mission concept or trajectory concept that exploits deeply gravity assist. Let me just take the gravity assist in the widest sense of the term, low energy transfers, which means orbits in the circular stiffity body problem, and the low thrust propulsion. And the idea is to have a trajectory that takes a spacecraft of medium to low mass compared to Cassini to explore closely the inner larger moons of Saturn, that are Dione, Tethys, Enceladus, and Mimas, in a way in which the spacecraft is weakly captured in orbit around these moons, and to do so in an efficient way and in a way that is compliant with existing and with the limitations of existing propulsion and power technologies. The strategy is subdivided in three parts, which are also the parts of the talk. So the interplanetary portion, with arrival at Saturn with a velocity relative to the planet of 1 kilometer per second, followed by fully gravitational capture and low thrust descent to Dione, where the tour starts, which allows to visit Dione, Tethys, Enceladus, and Mimas in this order. Okay, so just to put you in context, this is the system I'm talking about, Mimas to Dione. The 4 moons are orbit Saturn deep inside its gravity well in the E-ring between 185,000 and 377,000 kilometers. As a reference, Rhea is outer, a larger distance, 527,000 kilometers, and Titan is at 1.2 million kilometers. Okay, so let's talk about Cassini-Huygens first, because Cassini-Huygens has been the only spacecraft that has achieved orbit insertion around Saturn. This is the interplanetary trajectory, which was based on gravitational assistance of planets and chemical propulsion. It took Cassini-Huygens to Saturn in 6.7 years with a hyperbolic access speed of 5.7 kilometers per second. After that, in the pericenter of the arrival hyperbola, which was at 20,000 kilometer altitude above the surface of Saturn, it performed the orbit insertion maneuver, which burned 800 kilograms of propellant and applied 622 meters per second delta V. We can see the same maneuver again in this other figure. Yeah, we see the arrival, pericenter, and the first elliptical orbit, which was very eccentric, 0.98 eccentricity and 10 million kilometers semi-major axis. This is the orbit of Iapetus, and Titan is probably here. Then the tour started, which lasted from 2004 to 2017, consisting in many orbits around Saturn, 300 orbits approximately, with several flybys of Titan and also the other major moons and the inner moons in particular. You see here a sketch of the collection of the orbits followed by Cassini-Huygens. The spacecraft at launch had a mass of more than 5 tons, of which more than 3 tons were fuel. Okay, so if we want to, let's say, take the exploration of this system to a next level, and we want to study in detail the features that Cassini observed in these moons, we need to orbit them. But it's extremely challenging because these moons, as I said before, are deeply inside the gravity well of Saturn, so it takes a lot of energy or propellant to get captured around them. This is something which is unfeasible with chemical propulsion. So the idea that we have proposed is the following. Let's start from the interplanetary trajectory. So we start from Earth. And the trajectory that we have designed is based on low thrust and gravitational assistance of the planets. We have designed and optimized the interplanetary trajectory using the global optimization tool Multi-IT developed by Morante, Sanjurjo, and Soler in 2019. Actually, it was the topic of the thesis of David Morante. It models the dynamics with the patched conics in the plane, so it's two-dimensional, but the positions of the planets are determined by their ephemerides. And it works in 2 steps. I will skip the details of how the optimizer works for the moment. We can go into detail if somebody is interested. But essentially, the result is that we have obtained is what is shown here. This is the trajectory from Earth to Saturn. It's an Earth, Venus, Venus, Earth, Saturn type of solution, where the low thrust is applied in the arcs that you see in the thicker line. Note that the initial mass of the spacecraft is just 1.5 tons. The transfer time is from Earth to Saturn is 12 years, and the propellant mass that is consumed in this transfer is approximately 1/3 of the initial mass of the spacecraft. So we have a propellant mass ratio of 0.3 something. It is constrained, and it actually achieves V infinity at Saturn of 1 kilometer per second, which was what we wanted to obtain, and I will explain why in a moment. And the thrust level and the specific impulse of the thruster are compliant with the parameters of a Hall effect thruster developed by Safran. In particular here, what we try to do is to minimize the thrust because of the limitations that we have in terms of power production. When we are so far from the sun, we have to rely on radioisotope thermoelectric generators. So in other words, here, of course, we are constrained by the convergence of the optimization on the one hand, but on the other hand, we try to not to extend too much the transfer. So we cannot go to very low levels of thrust, and we don't want to exceed too much because we don't have so much power on board. Okay, so after 12 years, we arrive at Saturn with this velocity, which is much lower than what Cassini had. And we had realized when we did previous work with Jesús that was published in 2020 in the Journal of Guidance, that with such a low hyperbolic axis speed, you can achieve a similar orbit insertion at Saturn as Cassini, so at the same height with respect to the surface, with just 130 meters per second delta V. But here in the work that I'm presenting, we have made one step further. That is, we can do the orbit insertion without using thrust. And this is the strategy that we have developed. So this is the arrival in purple from interplanetary space with this hyperbolic axis speed, and then the spacecraft follows. It performs 4 resonant gravity axes with Titan. Here we model again the trajectory with patched conics in 2D. And so you see the spacecraft captured already after the first passage through Titan, where it enters a resonant orbit 1 to 5 with Titan. it returns to Titan and it gets into this new orbit, which is again resonant 1 to 2, and then at the third passage, it goes into a 1-to-1 resonant orbit with Titan, and eventually at the fourth passage, it is left in this elliptical orbit, which has the pericenter at the altitude of Dione. It is eccentric, but it is already taking us very close to the system that we want to explore. It takes in total 128 days to perform this transfer. And at this point, we are ready to descend to Dione. And this is done with low thrust. So we use the same propulsion system that we had in interplanetary space. This was the initial orbit after the last gravity assist with Titan. And we aim at this orbit in red, which is almost circular. So we almost circularize the orbit. But what we target is a Lyapunov orbit around the L2 point of Dione. The reason will be clear in a moment. The low thrust is applied all over throughout the transfer, and the guidance law is determined by a local optimizer, where we apply the steepest descent to an error function that essentially expresses the difference between the initial and the final, the target orbital elements. So you see here how the eccentricity and the semi-major axis decrease over the transfer. The initial mass was just above 1 ton, which was what was left after the interplanetary trajectory. It takes 4.3 years to perform this transfer, and the mass consumption is 300 kilograms. So at this point, the tour starts. And the tour essentially is conceived in this way. Here are the 4 moons, Saturn, the ring, and the tour is divided in essentially, it alternates 2 phases. One is the let's say are the intermoon transfers, these dashed lines with the arrow that are calculated in the Saturn spacecraft body problem with low thrust. So again, we use the propulsion system in this phase, and the science orbits around the moons which are designed in the circular restricted body problem of Saturn and each moon separately, and they are essentially homoclinic and heteroclinic connections between elevation point orbits around L1 and L2 in each system. Okay, so for the building blocks of both phases, the science orbits and the intermoon transfers, are planar Lyapunov orbits. We are in 2D, so we use planar orbits, and here you see 2 families of 50 orbits around L1 and L2 in the Saturn-MIMA system. The reason why we have families is because we wanted to explore different energy levels to optimize the tour as much as possible. And the other important element, are the hyperbolic stable and unstable invariant manifolds of these orbits, which are the key ingredients in the construction of the science orbits on one hand, and the intermoon transfers on the other. The separation between science orbits and the intermoon space is represented by the sphere of influence of the moon, which you see here, represented here. And essentially, this acts as a Poincare section, like shown here, where I'm sketching a transfer from Dione to Tethys, so 2 consecutive moons, using a hyperbolic invariant manifold, unstable manifold around L1 in the Dione system to depart, and arrival and a stable hyperbolic invariant manifold around L2 in the Tethys Saturn system. So here we collect the states of the spacecraft, and we use them to calculate osculating orbital elements of elliptical orbit relative to Saturn. And therefore, the problem becomes that of transferring between elliptical orbits, departing from Dione and arriving at Tethys. Again, we use low thrust propulsion, and the reason why we do that is because the invariant manifolds of different moons don't overlap in space. There is an energy gap, but in addition to that, there is a space gap. So we need to use propulsion, and we do it all the way through the transfer by using again a local optimizer like the one that I mentioned before when talking about the descent to Dione, where we minimize the difference between the orbital elements of the departure and the arrival orbit. So by trying different combinations of Lyapunov orbits and different combinations of trajectories on the manifolds, we have been able to design transfers which are optimized in this sense with respect to mass consumption and transfer time. In this case, it's the same. So we start the tour with an initial mass of 700 kilo, which was what was left after the descent from Titan to Dione. And for the different segments, Dione to Tethys, Tethys to Enceladus, Enceladus to Mimas, what you see here are the delta V's applied, the delta T, the transfer time in days, and the mass consumed. And the last line shows the totals. So it takes about 2 years to transfer from Dione to Mimas, and I haven't talked about the science orbits yet. So only considering the moon-to-moon transfers, and this transfer uses overall 125 kilograms of propellant. So the spacecraft is left at the end of the tour with 577 kilograms of the initial 1.5 tons. Last is the science orbits, and here I'm only showing how we construct heteroclinic connections on the same Lyapunov orbits and hyperbolic invariant manifolds that we use for the transfer between moons. It's just that we are using the other branches, the inner branches. So here an unstable invariant manifold and a stable invariant manifold of 2 Lyapunov orbits that have the same energy. And we seek, this is Enceladus, so this is the Enceladus-Saturn circular restricted body problem. And we identify the transfer that is characterized by minimum cost at the connection, which is this point here, the green asterisk. So these heteroclinic connections can be carried out at essentially virtually zero cost. This we are able to calculate transfers with less than 0.1 meters per second delta V at the intersection here at the impulse. As you see, time of flight from one orbit to the other is 46 hours. In general, this is the order of magnitude, 2-3 days, with a close approach at the moon. And this allows close observation of the surface. So this is, for example, the coverage provided by this orbit on the surface of Enceladus. This is the longitude-latitude map. And what you see here in the different colors is the coverage in hours that is given to different areas. So these solutions are extremely convenient because, first of all, they include the gravitation, the perturbation of Saturn, so they can easily be refined to a higher fidelity model. Lyapunov orbits, the Lyapunov orbit can be approached or left almost for free. So these are, let's say, virtually propellant-less transfers. They can be repeated as many times as desired, thanks to the autonomous character of the circular restricted body problem. These orbits, the Lyapunov orbits, are actually gateways between let's say the transfers, the intermoon transfers, and the science orbits. They can be used as parking orbits between phases. And as I said, they are not, as I said, these transfers can be repeated as many times as needed. So we can repeat the observation of the moon many, many times. So overall, I'll get to the conclusions. We have designed a complete trajectory concept that takes from Earth to science orbits that are weakly captured around each of the 4 moons. It takes 12 years of interplanetary journey to get there. Plus 6.5 years to complete the mission without considering the days spent observing the moons, which can be extended as needed. The total mass consumption, mass variation, is from 1.5 ton to just above 500 kilograms. So we spent 66% of the initial mass. And we believe that in this way, which is this strategy, which is compliant with existing technology and tries to optimize and let's say maximize the use of the gravitational assistance, can be a good basis to reach a real mission scenario in the near future. That's what we hope. So I will leave you just with reference to the three papers that I mentioned, in particular the paper that we published in the summer in Communication in Linear Science Numerical Simulation that tells the full story about this idea. And on a non-technical ground, I would like to express my gratitude to Jesús for these many years of collaboration and friendship. And I wish you to continue for many, many years, many other years working and collaborating with us. You're not getting away with it so easily. But most importantly, I wish you to enjoy life and time with your family, with your friends. These photos were taken during the last Ramadan in Abu Dhabi, at April this year. And I wish you to stay healthy and happy like this. Thank you very much.
Thank you. Thank you very much, Elena.
Welcome.
I don't know if questions or comments. The Jupiter gravity assist is not allowed.
Okay. We have tried trajectories which include Jupiter gravity assist. The problem is that with the constraint we have, 1 kilometer per second arrival, the boost that the Jupiter gives you takes you essentially away from this outcome. And in other words, for the moment, for the results we have obtained, give us longer transfer time if we include Jupiter. So it's not efficient in this situation. It's not convenient.
Okay, thank you.
Thank you.
Sì, sì. Hello, good morning, everyone. It's a real pleasure to be here. Just as a forward, it's a great honor for me to be a speaker in this workshop dedicated to Professor Jesús Peláez, because he played a major role in my development as a scientist, as a researcher, as well as Enrico, who's also here. Probably they were the most, for my career, they were the two most important people, persons. Just to give you I'd like to mention some history. I met Jesus in the summer of 2001 as a graduate student visiting Enrico at the Harvard-Smithsonian Center for Astrophysics. I have 3 vivid memories from that time. How Jesus taught me asymptotic perturbation theory. I was sharing the office with him and was working on some interferometric problem and dynamics. And I remember I figured out there was a zero-order solution, and he came up to me and I said, "But you can get the first order. You just do an expansion with it." I said, "Wow, this is magic," but I never knew that this was possible, because I was an undergraduate student, but these things are not taught even sometimes at graduate level. So I said, "Wow, this is magic. It works so beautifully." And I say, "Well, it will be a tool that I will enjoy for the rest of my career." And in fact, it was like that, as I will show you later. Then the other thing is that he presented a regularized orbit propagation called DROMO that I didn't even understand at that time. I was barely dealing with Cowell propagation methods, and that's as far as I could go. And he presented this method where time was not a dependent variable. It was an independent variable. There was quaternions and so on. It looked to me like black magic at that time. I would not know that later on I would work on that same stuff. And then I remember that he came and the big thing was electrodynamic tether instability, and he had discovered like a key instability, and there was a big publication at that time, and that was the one of the main research activities he was involved in, and so I learned about that at that time. And the last thing it was, I still remember the secretary was Linda Williamson. I miss her a lot because she was a wonderful person, and she before Jesus arrived, I said, "We are so glad he's visiting us again." Wow, that must be a very nice person to be in touch with, and in fact it was like that. So a few years later, as a postdoctoral student at ISA Aztec, I was delighted to collaborate with Jesus and his team, including Martin Lara and Enrico, on tether dynamics at the Lagrangian points that Martin so beautifully explained, and it was like a fascinating topic. Finally, starting in 2009, had the privilege to join the Grupo de Dinámica de Tethers in Madrid and be part of Jesus' team. And I've been here ever since. So there are many, let's say, inputs that I received from Jesus in my career. One of them, and maybe possibly the most important, was about Dromo, the propagator I just described before. So Dromo is basically a formulation, mathematical formulation to propagate orbits in an efficient way. What does it do is exploits two main concepts: the ideal frame, introduced by Hansen and then explored by Dupree, a slow evolving frame attached to the osculating orbital plane, so the angle variable, as Martin would call it, and the fast action variable in that model is a fictitious time that evolves fast as a fast evolving independent variable. The independent variable is an angle, so that complicates things. When you try to understand that, so he has been put forward by Jesús Pelaez in 2000. Is inspired by previous work of Dupree, Palacios, as well as Sid and Sansaturio. Now, apart from being an efficient way of propagating orbits, because it reduces numerical error times CPU time, basically, either you are extremely fast with an acceptable error, or you are extremely accurate with a little bit of more propagation time. But it can be exploited also as an effective change of variable scheme to obtain approximate analytical solution of fundamental astrodynamics problem. Similarly to the basic change of, let's say, from true anomaly to eccentric anomaly that allows you to get to Kepler's equation, which is the most beautiful equation for many people in astrodynamics. But similarly, you can exploit this mathematical formulation to manipulate basic astrodynamics problem, and I did that first in collaboration with Jesus, and then also on my own. And I thought it was very advantageous, and it was a key to my career. As an introduction to Dromo, I took this from Jesus' classes. He teaches Dromo. He used to teach Dromo at the astrodynamics class that now I inherited from him. So basically, is a method proposed that he proposed, you exploiting the heritage of big figures in astrodynamics like Dupree, as well as other major researcher like Palacios or Sid, so basically these were the heritage, but he was the one that put everything together and formally produces a formulation that makes sense to itself and was well explained when it comes to code a propagator. So he made a test and he showed that it works, and so it was ready to use, let's say. And at that time, I took it and I tried to analyze it, and I spent many months to get all the details because it's complicated stuff. But once I got how it worked, then I could use it for my own work. So one simple thing I will mention today, and is the major input for the rest of many of the works that I did, is that let's only consider the planar Dromo. Let's see, we are only in the orbital plane. We do not have out-of-plane perturbations. So the state is described by 4 variables. The quaternions go away, and then we only have what we call here Q1, Q3, Q3 variables that describe how the shape of the orbits and the orientation of the eccentricity vector in the plane varies. And then we have time as a dependent variable. When then there is a mysterious theta variable that is the independent variable that describes how the ideal frame moves. But in the planar problem, it's actually quite easy because it's basically the angle reckoned from the initial eccentricity vector. So the true anomaly plus a drift beta, which is the result of all the perturbation acting. So we have a 4-dimensional state vector, and the equations of motion are quite compact. They're written in this way. And this is the transversal velocity. All the other quantities these are the radial and transversal force per unit mass. And this is the equation of time, which is a Zundman transformation. So how about exploiting this to, the first thing I did was, let's look for an approximate solution for the constant tangential thrust problem, which was dealt with by previous researchers, but the thing is that the oscillatory evolution of that solution was not known before. So I thought there was something more to do. And I said, well, also in collaboration with Jesús, we wrote the equations of motion of the tangentially perturbed motion in this way, where epsilon is the magnitude of the thrust and is, of course, along the tangential direction. And remembering what Jesús taught me in Boston, I said, well, let's crank up perturbation theory. All our elements are a zero-order state, which is the Keplerian state, plus epsilon times the first order, and epsilon is the magic small parameter that appears in the equation. So the zero order is the Keplerian states where all the elements are constant, and the time obeys Kepler's equation. And the first order was this equation here that can be integrated by quadrature if you made a substitution that resembles the true to eccentric anomaly transformation. And by doing this and using Maple or Mathematica, I was able to obtain this solution where this function, complicated function here, can be split into a secular and periodic part. And the secular one, not surprisingly, is made up by complete elliptic integrals of the first, the pendulum, and the second, the ellipse perimeter kind. These are basically the terms that appear here. These are the slow variables, the shape of the orbits. Time will come on the next slide. And yes, so it was nice to see this kind of secular contribution with a, of course, function of the eccentricity, and have a solution like that. Then he came to the time to see if we could figure out how time is affected. Of course, the 0th order is the Kepler time, let's say the one that Kepler's solution, Kepler's equation provides you, but then there is the 1st order, the one that perturbations are shaping. And a similar differential equations by expanding basically the Zundman transformation of Dromo was obtained in this way. And this was also hard to integrate. And again, the transformation to eccentric anomaly played a key role in obtaining, again, a solution. Solving by quadrature, again, harder than before, but still Maple can help you with that. And separating again oscillatory and secular part, we can get to this compact solution where the T function again are secular and oscillatory, and the secular, not surprisingly, they again contained elliptic integrals, K1 and K3, the same functions I showed you before. And you can see, not surprising, there is an E square. Then there is a linear term which is mixed with oscillatory terms, so it's like secular but oscillatory at the same time. And then one thing to admit is that these are periodic functions that are truncated Fourier series. So in this case, we do not have a closed form solution. We have a truncated in eccentricity. But the important thing is that the main, the strongest evolution, the square of E, and the linear one, well, this one is closed form, and this one dies down in the long run. So it is a very useful solution. And we plug into some challenging problems. This is a GTO orbit raising with constant low thrust, and you can see here the numerical and analytical solution. They agree beautifully. Of course, if you propagate for longer time, the first order solutions departs from the true solution. However, I mean, it can still retain the quality. Sorry. Well, the other thing is that I did, again, exploiting Dromo, is the D matrix. Basically, I was looking for a spatial state transition matrix, but that used time as a state variable instead of as independent variable. Again, took the Dromo idea, which is symbolized by, schematized here. Basically, you have a nominal trajectory, you have a perturbed trajectory where you give velocity and radial error, and you move forward in time, you check what happens at different angle, and you do like a Poincaré section. You end up here, you cross the Poincaré section here with an error in radial, velocity, and time. So the important thing is that you do not go around here. You go on the section. That kind of formulation allows you to get a much more linear behavior when it comes to construct a state transition matrix, as I will show you later. Basically, you propagate the error in a linear way. I skip this. The matrix looks like this. There is an in-plane part and out-of-plane part. The computation of the partials, again, is made easy by using Dromo theory and the transformation, because they are very convenient also for basic partial computation. The terms look, the trickiest terms are the one that describe the time delay error in terms of error in velocity and radial and transversal velocity. Anyway, there are other terms. You can check it on the article. But what I want to show you here is how it compares to the classical Cloisi-Wiltshire or Yamanaka-Ankerson state transition matrix. We are dealing with Keplerian motion. So theoretically, if the state transition matrix was perfect, orbital elements would be preserved. So one way to see how good the transition matrix is do they maintain the constancy of the orbital elements? So we introduced a Keplerianity valuation and check how the semi-major axis is varied. For example, we took exactly the Yamanaka anchor as an example, the highly eccentric orbit, and we see that our solution preserves orbital elements in a better way. So the Keplerianity is preserved in a better way, so we obtain an advantageous, an improvement with respect to the Yamanaka anchors. We use the same matrix to construct a analytical Lambert solver, approximate but quite accurate, as you can see here. We have implemented this in JavaScript with the help of Juancho, and it's available online, so you can now construct pork chop plots in an easy way using internet, basically. And also, last but not least, we have been discovering another useful application of the D-matrix formulation, and this is the last slide, to obtain what is called a reachability domain, meaning low thrust reachability domain. You have a spacecraft, you have low thrust, you allow to thrust along a certain orbit arc along all the possible directions with constant low thrust, and you want to know how far you can end up. So in this case, we end up in this like snake-like domain, and the D-matrix is key because it gives you the primer vector, the approximate greedy primer vector, where you should thrust to maximize time delay and radius. And we demonstrated that a good approximation of the reachability domain is a combination of maximizing time delay with respect to the normal orbit, which basically moves you around here, and radius, which basically gives you the width of the domain. So basically, this is a work in progress, but it has been presented recently by a student of the group of Armelin in New Zealand, in Auckland, where I've spent some time there, and we worked together on this problem. That was really, really nice. And I think with this, I conclude. I hope I hadn't taken too much of your time. I'm really greatly indebted to Professor Jesús Peláez for his tremendous contribution to the field of astrodynamics, as well as his guidance and inspiration. In particular, in my case, I think his seminal work on regularized orbit propagation was a key starting point for the most relevant contribution to the field I was able to achieve myself, humbly, with my own contribution. I hope to continue with that. And like many of his former students and many of his collaborators here, I did and will keep doing my best to follow his example and continue his legacy. Thank you, Professor Peláez. Yeah. Yeah. That's true. That's true. Yeah, that's true. And in fact, Giulio was also working on Dromo and came here, and he knew nothing about it. And I remember that Jesus gave to him the yellow book of Stiefel and Scheifele to study, and he was going down the library and working hard on the problem. And in fact, he constructed his career on starting with that. Yes. Yeah, the legacy continues. Yes. Thank you.
Hello. Dan Shear is giving my greetings to everyone in attendance there at this celebration of Jesus's academic work and career. I'm very sorry that I can't be there, but I have a complicated travel schedule this week, and the timing doesn't allow for a live presentation, even virtually. So I'm sorry that I can't be there to enjoy all of your company, but nonetheless, I'm very happy and proud to be able to at least talk a little bit about my interactions with Jesus, and just talk a little bit about some of the collaborations that we have had in the past. And specifically, I'll talk a bit about the design and dynamics of tethered observatories in the Jovian system, which is some work that we collaborated on. So in the past, I've actually had opportunities to collaborate a number of times and have Jesús Pelaez visit me at my various institutions. So the first time was in the summer of 2006, I believe, sort of reconstructing what that time was. That's quite a while ago now. And at the time, I was at the Department of Aerospace Engineering at the University of Michigan. And he visited me and we spent, I think, at least a month or two together discussing and collaborating on developing a model for a model that would analyze the dynamics of a self-balanced tether in the Jovian system. Resulting from that collaboration were two papers that were actually published sometime after that. But a lot of the work that we initially did was firmed up in that first visit, both in the Journal of Guidance, Control, and Dynamics. And then the second time he visited was much more recently, just in the spring of 2020. If you think back to the spring of 2020, there were many other things afoot in the world. At that time, I was no longer at Michigan and actually had moved to the Department of Aerospace Engineering Sciences at the University of Colorado. He visited me there, and I think was here for about a month, and we were just starting to focus in on some collaboration. We had some questions and some activities related to some of the work he's done on Lambert's problem and other interesting problems with the MOID and the like. But unfortunately, right in the middle of March 2020, the COVID sort of stopped in-person meetings. And in fact, he had to go back home later in March per his university's direction. So unfortunately, that collaboration period was cut a bit short, and with so much additional confusion and activities going on at the same time as COVID, we never really had a chance to sort of get deeper into the problems that we started to talk about. I have been very pleased in the past to have members of Jesus's lab visit me at various times. In particular, I think about the visit of Manuel and the visit of Jode, both of which were very fruitful and ended up in some nice papers and really some nice connections between our lab and the lab in Madrid. So I'll just talk at a very high level on these tether observatories at Jupiter. Jesus is by far the much more the expert in all the detailed physics and the interesting applications that they can be used for. But I found it a very enjoyable collaboration and sort of opened my eyes to different sorts of dynamics and different opportunities that exist, even if they are a bit futuristic now. So as you probably know, the strong magnetic field of Jupiter actually enables some very novel applications of electrodynamic tethers for creating sort of permanent observatories that are powered by the environment in which they're placed in equilibrium at. So in 2006, we collaborated on developing a consistent, useful dynamical model to analyze these ideas that he was talking about. We combined several elements together. First was have an appropriate model of an electrodynamic tether in orbit within the Jovian system. Next were development of dynamical equations accounting for the attraction of a Jovian moon, the perturbation from the Jovian gravity, force generated by the tether, and the dynamical coupling of attitude librations of the tether with the translational dynamics as well. And coming out of this analysis, we were able to find the existence of families of equilibrium configurations and analyze their stability and actually find some that were in fact stable, opening up these to potential practical applications. I'm not going to dig into a whole lot of detail, but just to present some of the most important results, I think. What we found is that for a tether placed close to a Jovian moon, the Hill approximation in celestial mechanics is valid and allows for a simplified version and accurate version of the CR3BP, circular restricted three-body problem, to be posed. We were also able to incorporate into this the translational and rotational forces, torques acting on the tether in this environment. And the model becomes very simple, and it's stated here with these 5 differential equations. So there's the in-plane dynamics, and here you see the classical Hill three-body problem terms with traction along psi and eta, and these additional terms that actually account for the force of the tether that the tether can provide under the appropriate assumptions for current flow and all that. These equations, of course, are stated in a rotating frame. The attracting mass here is actually the Jovian satellite, and the effect of the Jovian gravity field, or of Jupiter's gravity field, is actually encapsulated in the single tidal term that acts along the direction to Jupiter. There's also an out-of-plane oscillation that exists, again modeled exactly here from the Hill approximation. And we didn't incorporate any possible out-of-plane terms, although I think they could have been. We also have, for the attitude control of the tether, we have an in-plane pitch angle, theta, with the associated dynamics. This too is, I believe, stated in a rotating frame. And we also have a nutation or out-of-plane angle for this observatory as well, or this tether as well. And these are some of the specifications here. So, as I said, the equations are stated in a rotating frame. The tether is treated as a rigid body. We did check to make sure that it should be under tension and there's no compressive forces and the like. So that was actually validated. And we assume it can generate thrust and control torques. This parameter psi is important, and it's a non-dimensional measure of the electrodynamic force that is generated by the tether. So these are the equations that we derived and then analyzed. The main focus, and maybe the most interesting aspect of the papers, was to find the existence of equilibria. And in fact, what we found is that the tether can balance the electrodynamic force against the attraction of the moonlet. Here you see the moonlet, here we see the tether, to find an equilibrium position and orientation. And there are actually whole families of equilibria solutions that we were able to find. I'll just talk very briefly about the simplest one, where the tether is just displaced behind or in front of the Jovian moon, and the tether is aligned so that essentially it points towards Jupiter. this provides it with the appropriate current to actually generate the force to maintain this position. And in this configuration, the system can be completely balanced, creating a long-term station for observing the moonlet, perhaps, and for Jupiter, and also generating significant amounts of power that can be utilized for many other purposes in this system. At the time, we were actually comparing and contrasting this with the JIMO mission, the Jupiter Icy Moons Orbiter mission, which was looking to send a very large nuclear reactor, essentially, in space to go visit Jupiter. And I think here Jesus was able to show that the power generation from the tether was in some ways much more efficient, as you might expect. So we found equilibria. More importantly, we wanted to look at the stability of these equilibria. And we looked at translational and rotational stability of these equilibria. We were able to show that the out-of-plane nutation and oscillation were both stable or oscillatory across the spectrum of different force values that we were looking at. And in fact, the force value, the non-dimensional force, was essentially the main parameter that drove the location and orientation of the tether at these various equilibria. And then we also analyzed the in-plane coupled translational and rotational stability. And we were able to find situations where there was stability and instability. Maybe the most practical aspect of it was that we were able to find that the system is stable for a given interval of non-dimensional force. And this is shown here. Here we're plotting the real eigenvalues of the system and the imaginary eigenvalues. And what we see is for very small up to some finite non-dimensional size, a little over a tenth, we actually had stable dynamics. So stable out-of-plane dynamics and then stable in-plane dynamics, so that if you perturbed this tether as it was operating, it would just have just oscillations. As we crank up the force more, you can actually, I believe here, bring the tether closer and closer to the Jovian moon, because you're generating more force, so you can counter more of the gravitational attraction, but it's at a cost of losing stability. And what we see is that the first transition, the eigenvalues hit on the imaginary axis, and then they break off, and we have actually a fully complex situation, which is obviously unstable. And then as you increase these even more, they eventually, we have some of these eigenvalues come back onto the real axis. However, and then they have hyperbolic instability as well. So it becomes quite unstable as you increase that force, non-dimensional force term, and it would really require some additional control to actually stabilize this motion. It should be stabilizable, however, but we didn't look into that. So some quick conclusions. So this analysis actually showed the feasibility of in my understanding of it, of a permanent electrodynamic tether in the vicinity of the inner Jovian satellites, such as Metis. That was one particular one that we looked at in detail. This observatory would also generate lots of excess power, which is then available for scientific or exploration purposes. And in a follow-on paper, we were actually able to use these same derived equations to allow for a dynamical analysis of spinning non-electrodynamic tethers. And it was shown by Jesus, mostly. I had limited interaction on that paper, that you could actually take otherwise unstable orbits, such as a halo orbit here, or these vertical orbits here, and stabilize them by appropriately spinning this tethered satellite, in sort of analyzing conditions under which this was possible. So that was a very interesting outcome that came from this paper as well. This is the presentation I just wanted to contribute. I thanks very much for the opportunity to at least have a virtual presence at the meeting. Please have a glass of wine for me, and I look forward to seeing many of you in the near future. So with that, I want to thank you again and give my greatest congratulations to Jesus and honor him for the astounding and impactful academic career that he has had. With that, thanks very much and goodbye.
Hola, yeah, sí. Okay, so thank you very much to Manuel and Martin for pushing towards the organization of this event. And I'm very grateful to be part of this celebration to such a milestone in the academic career of Jesus, as it is his retirement. Usually it's something you do once in a lifetime, so it is definitely a memorable moment. Okay, so in my talk I'm going to revise some of the things that make the Dromo formulation important in terms of the legacy it implies and it leaves behind and the many works that it has led to over the time. Yes. Emanuel Lasker was chess world champion for over 25 years. He used to say that when you see a good move, then you should look for a better one. And this kind of summarizes the storyline behind Dromo. Dromo might be seen as an example of looking for the better move, or the better way of propagating orbits. As many things in the career of Jesus, this all started around tethers. As far as I've been told, the story goes as follows. Back in time, when Jesus was doing complex tether dynamics simulations with flexible tethers that basically using models that imply many different nodes, each of which has to be propagated. So the problem seemed to be that when the number of particles raised to high numbers, then the simulations seem to get annoyingly slow. So that's when Jesus might have thought there might be a better way around this. There might be a better way of getting this propagated faster and more precise. And that's what led to the development of the Dromo formulation. I'm of course going to skip all the equations of the development, but it suffices to say that Dromo is based with basically it's built like an artisan plays with maths, shaping, formulation that basically combines wisely techniques such as regularization, linearization, and perturbation techniques. And as a result of doing all that mathematical trickery, Jesus managed to reach a formulation that had very interesting features, very useful properties, such as all the variables except one being orbital elements. It had redundancy thanks to a quaternionic formulation. It is in principle non-singular, of course, as long as you have the angular momentum defined, which is the case almost always. And the formulation was universal in the sense of being applicable to all sorts of orbits. At first, it seemed like a very good and well-performing propagation scheme, but it was even better than that. It was a gold nugget that it basically took several years to grasp all the different implications that there were underneath this formulation. Before going there, Dromo has another advantage, that is that it's from a geometrical point very easily describable. It's very easy to see what the different orbital elements mean. For example, if we take any random orbit, let's assume for simplicity an elliptic orbit, at the initial time we can take a look at what its orbital plane is and just attach a reference frame to that orbital plane. Just make sure X and Y are on the orbital plane. Well, that gives us a freedom to choose what this arbitrary parameter sigma, which is an angle, should be. It turns out to be wise to nullify that angle, just make it 0 by default, because equations will end up looking much nicer, and thus align the x-axis with the initial eccentricity vector. As time evolves and the orbital perturbations basically change the orientation of the orbit, the orbital plane itself will be rotated. That rotation can be parameterized conveniently using a rotation matrix that can be transformed into a quaternion. Those quaternion elements give rise to the first 4 of the orbital elements of this formulation. Then it remains to describe what the orbital motion within the orbital plane is evolving like. The orbit within the plane will basically rotate, will get larger, smaller, change eccentricity, and so on. So basically, the osculating eccentricity at each instant of time can be identified thanks to this beta angle with respect to the frame attached to the orbital plane, and we can wisely combine the eccentricity and the beta angle as well as the angular momentum to define these 3 geometrically very meaningful variables that are basically the projections of the eccentricity vector over x and y and the inverse of the angular momentum. So these are the other 3 angular variables of the Dromo formulation, and the last variable is one that allows us to track the motion of the particle along the orbit. So once the orbital shape is defined, the particle will circle around the orbit, and that angle sigma needs to be related with time, and this is accomplished through a time regularization. So in brief, we have this set of 8 differential equations that have a very nice structure because they manage to decouple what happens to the orbital plane, what happens in the orbital plane, and that gives a natural way of separating those 2 movements, so dynamically very, very powerful, and then how the physical time evolves with that independent integration variable that we call sigma. These equations need to be integrated with some additional definitions, and that's it. So as I said before, it took many years to realize what the deepest implications of this formulation were, and also how it linked to the seminal work of some of the glorious names we can find in the literature of astrodynamics. One of those names happens to be Hansen, which long time ago he defined a concept that he named ideal frame. As it turns out, the quaternions that Dromo formulation employs happen to define an ideal frame. So this wasn't sought for. This instead naturally emerged when Jesus made his mathematical artifact to develop Dromo. But it is nice to see how 150 years later, something independent development matches with a concept that was probably long forgotten for most people in the community. So it's a way of rediscovering something very useful that might otherwise have gone unnoticed for many more years. These ideal frames have properties that are possibly one of the things why Dromo is so performant, why it performs so well numerically. And there's another work to which Dromo links that it was pointed out for many years, but it took us a while to realize what the connection was between the Dromo formulation and another formulation proposed by Dupree and another version that later Palacios et al. Presented. So they happen to have many analogies. They all three rely on the concept of Hansen's ideal frame. So 4 of those orbital variables happen to be the same. Then to describe the motion in the orbital plane, that's where differences emerge. They all use somehow the angular momentum, but then for the orientation and eccentricity and the shape, that's where Dupree presents different set of orbital elements that are related to the ones of Jesus. Palacios goes a different way. And another difference is that Dupree did not propose to use a time regularization, and Jesus did. So, therefore, similarities are there, and it is also notable how, again, formulation independently developed links back to a work done by such magnificent figures as Dupree himself, and that for some reason or another have gone had gone under the radar for most of the astrodynamics community. So one of Jesus' achievements is to bring to life all these formulations and relations. Dromo has gone a long way since then. For the last 15 years, since the Dromo paper was published, there's been a series of additional works with different versions of Dromo being published, modifications, improvements, both by Jesus himself and his collaborators. There's flavors of Dromo that are specific to either elliptic or hyperbolic orbits that make a trade-off to get some benefits. There's recently been proposed, like, why don't we try to reduce the size of the ordinary differential equation system by trying to embed the angular momentum within the quaternion by scaling it. There's also been proposed to replace the physical time by a time element and therefore have a Dromo version where all variables are orbital elements. Time regularization can be approached differently, trying to embed some energy or Lagrangian or equivalent stuff. Also perturbations might be inserted in potential form, and also it's been proposed perhaps using gauge theory to try to obtain some variant of Dromo that maybe leads to non-osculating elements. So there's a lot of things that have been done, a few that are still to be done. Dromo has accomplished what it was intended for when it was created, and it proved to be a computationally very performant orbit propagation scheme. In all the various tests we have done, like this is, for example, calculation of a ground repeating orbit. This is a constant radial thrust problem. So in all of them, Dromo has been sometimes the best, not always, but in all the cases, it's been consistently among the best performing methods out there in the literature. So it is quite something. that that method has had such an impact and good result. Other subtleties that arise with this formulation when numerically solved is that the physical time in this formulation is a dependent integration variable. The problem with this is that we usually like to integrate from an initial time to a final time. And the problem is in Dromo, time is a consequence of the integration process. So what we have to choose is what is the initial and final value of this fictitious time, sigma. Of course, they are both related, they one to the other. The problem is you only know that correlation as you are integrating your problem. So that leads to numerical integration errors, basically translating in the fact that when you think you're stopping your integration at the prescribed final time, in truth, you are stopping at a different value of the fictitious time. And that different value links to a different physical time, which is not the intended one, but is what your numerically computed equations are able to provide. And so this is important because Dromo manages, thanks to its geometric description and formulation based on elements, basically separates the orbital propagation problem in a geometric part that is very well described, very easily and precisely propagated. So it provides a high fidelity geometrical description of the orbit. So all the instabilities present in the orbital formulation, they all end up in the propagation of only one of the 8 Dromo variables, which is the time. So basically, Dromo is more precise than simulations say, only if we knew what exact value of sigma it is where we should stop. So if we knew in advance that value precisely, Dromo would be orders of magnitude more precise than it is. So perhaps here there is room for trying to squish a little bit more the performance of the method somehow. Other things related to Dromo that are still to come. For example, 10 years in the making, Jesús proposed to extend the principles of Dromo to the propagation of the attitude dynamics instead. This paper won the best conference paper award, but still it's on the drawer waiting to be finished and published. We'll get there soon, I hope. Other things that have been recently proposed is to combine Dromo with interval arithmetics. And it turns out, we already proved that instead of combining the integration in Cartesian space with interval arithmetics, if we first go to Dromo variable space, apply there the interval arithmetics, and then at the end of the integration go back to Cartesian space, the propagation of the error is much, much smaller, which basically implies that we have verified arithmetics that is much more reliable and more precise than when performed directly on Cartesian elements. So far we've attended the use of Dromo as a numerical propagation method. As it turns out, Dromo is equally suitable for analytical treatment, as has already been mentioned in previous talks today. And the use of these Dromo variables to tackle some of the classic problems in astrodynamics has proven very fruitful, as it has often led to, on the one side, exact solutions to known problems, but from basically often more insightful perspective, thanks to a more appropriate choice of variables and solutions that are easier to solve and more precise. So one such example is the constant radial thrust problem, for which exact solutions can be found thanks to Dromo, that have several advantages over other solutions proposed in the literature. There are also approximate solutions in which we can, for example, look at asymptotic solutions on the one side, and here, well, constant tangential thrust, main problem, and so on have been approached efficiently thanks to Dromo. And also, these approximate solutions can be obtained combining averaging and perturbation techniques that can lead to very interesting results. And again, it turns out that some of those results might already be known in the literature, but it turns out that when expressed in terms of the Dromo variables, they take another form that's often more compact, easier to identify and to get some insight and extract some physics from the equations. So a lot of powerful implications that come from the use of Dromo. And concluding remarks. How could we summarize all the legacy that the Dromo formulation has left behind? Well, on the one side, Dromo has left us with a cutting-edge numerical orbit propagation scheme that is very, very appropriate, very good, well-performing, and easy to implement. So that's already something that many people might find interest in applying. Also, the Dromo variables have been proven very, very convenient for analytical treatment, enabling to approach problems that are not so easily solvable with other choices of orbital variables. So again, still a long way to go along this avenue. More. Also, rediscovering and in a way also elevating to new heights the seminal works of great glorious figures of astrodynamics history as Hansen and Dupree, which is to say that it is my opinion that in the books of history, the name of Jesús Pelaez will now be linked somehow to other names like Hansen and Dupree, and that will stay there forever. More. The work of Jesús regarding Dromo has created some sort of revival of the interest in the astrodynamics community in the use of these regularized formulations. So I think it is fair to say that if it wasn't for the success of Dromo, many of us would not be here or would be here talking about something else. And many people that didn't even know what regularization is and are today using regularized methods themselves. So all of that is thanks to the pioneering work of Jesús. Actually, I didn't have time to gather all the bibliography to show the yearly distribution of publications related to regularization, but it peaks after a publication of Dromo. It took a few years to gain momentum, but afterward there's a gloom, a blossoming in the publications of regularized orbit formulations. And all that is for the trend that Jesús sent in the astrodynamics community into this direction. Then also to highlight that Dromo is just one of the very many impactful contributions that Jesús had to the astrodynamics community. So it would be hard to choose which one is more impactful than the other, because there's so many to choose from. And the best thing is, I know for certain that there's still more to come recently. And more. Also, all the legacy that Jesús made with his work related to Dromo, in a sense, becomes the heritage that people like myself and many others in this room, which we could be one of the next generations trying to make contributions to astrodynamics, will be able to build on and extend. And Jesús has showed us a way in which we can continue doing research for many, many years to come. So he basically opened the treasure chest in a way, and we are very, very grateful for that. So for all the contributions that Jesús has done so far in the academic domain, for all the ones he's still to make, and for all these years of working together and learning from Jesús, and still many more years to come. So for all of that, thank you very much, Jesús. Muchas gracias. And just to conclude, that both in terms of as a university professor, as an academic researcher, you are really a magnificent figure to look up to. And well, I just hope that when I'm done with my academic career, all the colleagues, collaborators, friends, students have an opinion of myself that's at least half of the one I have for you. So again, thanks for everything.
So, so the next presenter is Javier Roa, who is going to present from online, let's say. Thank you, Javier, because it's too early for you. So thank you for being here, and the floor is yours.
Hello, can you hear me over there? Okay, I see nothing faces. I cannot hear anything right now, but let me see if I can share my screen. I had to actually leave to be able to share. All right, hopefully you can see something on the screen. Okay, that's great. So let me go in and share again. Yeah, it's great to be able to at least participate remotely. I'm really sad I couldn't be there in person, just to celebrate Jesus and be with all of you that I can see over there on the video. It would have been amazing to get together again. But I'm hoping in a short time I'll be able to travel to Madrid again. But we recently had a baby, and yeah, it's a bit more challenging to travel now. But again, at least it's great to be able to present even if remotely. And in this talk, I wanted to talk a little bit about one of the applications that that came up from, well, many years of work with Jesus that I had the privilege of having. And of course, most of these applications have been how to use regularization to improve different solutions to different problems in astrodynamics. And the one I wanted to focus on today is uncertainty propagation. And I think it's safe to call it the Pelaez way at this point, because it's really really based on the groundbreaking ideas from Jesus on like how to exploit well all the nice tricks that Ole has been talking about before in like the foundations of Dromo. And there's a lot that can be done for in general like other problems in astrodynamics. And for this presentation, I wanted to go down memory lane a little bit, and I tried to find good pictures of the group, but unfortunately couldn't find any. So I would love if after this someone could send me some. I think they got lost in another computer. So I was hoping to have something more fun than Mars on top. So for now, that has to do like just imagine that's the group from like back in the day, because I would have loved to have a nice picture of all of us in there, maybe from a meeting or something like that. When going down this kind of archaeological trip for this presentation, one thing that I did find was the very first email that I sent to Jesus that was over 10 years ago, actually. The very fun thing was being a Gmail hoarder is that I could go in and like find a little bit of the story there that I didn't quite remember the details, but I have taken the orbital mechanics class with Professor Ramis, and that was during the fourth year, I believe. And I was really fascinated by orbital mechanics when I had that course. So then I sent him an email saying, hey, I could maybe collaborate with you if you have something going on. And then he was the one who said, well, I don't have anything, but you should reach out to Jesús Peláez, who he has like a very active research line. So then I sent him an email, and well, fast forward 10 years, here we are. And the kind of two things that struck me from this email is, first of all, like how excessively, kind of polite and pelota the email is. And then also the fun thing is that profile picture from there is probably from 2012 also. So it was also fun to see how things were back in the day. And the interesting thing is that the very first project that Jesus talked to me about was actually using Dromo for formation flying. And the lessons that I learned from Jesus in terms of relative motion back in the day, they have like really gone along with me for a long time. And even so, like in the last job interviews that I did a few years ago, some of the questions, I mean, I could answer them thanks to the work that I did with Jesus in relative motion and all the like long hours in his office, him explaining things to me. So, I mean, it's pretty amazing to see that sort of thing coming back. So with this work with formation flying using Dromo, we exploited one of the main ideas that Jesus had. He was convinced that because with Dromo, you use fictitious time, you are really isolating the time instability of orbital motion, like how things diverge because you have a different timing along the orbit. He was convinced that by exploiting that feature, that you isolate that time instability, we could get a better description of relative motion. And well, no surprise, he was right. And that works really well. But the really fun thing is that for this work on uncertainty propagation, I was using exactly the same thing. In completely different context, this presentation is based on some work that I did with Ryan Park maybe a couple of years ago, and we presented a paper at SciTech. But the equations are like the foundational equations are pretty much the same. I will try to show that in comparison with the ancient equations that we had back in the day. But I think it was really nice to see how those concepts, those ideas that Jesus thought would be like the basis of relative motion with Dromo actually work really well also for uncertainty propagation. So in this presentation, I would like to start talking a little bit about uncertainty propagation in this framework using like the core part of Dromo and time regularization, how that allows us to actually capture nonlinear effects. That's the main thing that we are going to do with this presentation. And then if we have time, how we can actually flag these uncertainty propagation in transformation scheme to improve things even more. So just kind of a quick slide on sort of propagation. The linear approach, kind of the linear way, is where we have a reference trajectory. Let me get a laser pointer here. We have a reference trajectory starting from some initial conditions, and then we perturb this trajectory. So we have a perturbed orbit now that we are going to track, and then at some future time we can check what's the delta that we have propagated over time. If we linearize for a small initial delta, well, we use the transition matrix that's just written in the first order part of the Taylor series function, and this has all the properties and goodies from the linear solution, where it's simpler mapping. The dimension of the problem is very contained. It's n by n, where n is the dimension of the state vector. And well, this is fast. You can just implement the first order variational equations in your propagator, and then you get the STM, the transition matrix, very easily at the time that you need. This, in practice, is affected by a kind of a fundamental property of orbital mechanics that the velocity is inversely proportional to the altitude. So if you have this secondary orbit is slightly higher, then it's going to be drifting backwards relative to the primary. And this specular effect appears even in like the kind of first solution to relative motion, the Cloffe-Wiltshire equations, where you have this contribution from the specular term, and then you have also periodic component, and then you end up with this very classic kind of bouncy relative motion solution. And there's no way to get away from this secular term except if you have energy matching orbits, but otherwise the orbits are going to drift apart. So that problem causes the linear solution, well, to start losing accuracy for either long propagation times or long separations, simply because this secular term is going to grow, hence the name. So what we are going to try to do is actually start capturing nonlinear effects. And there are many ways that you can capture nonlinear effects in uncertainty propagation. But for the purpose of this talk, we're going to use high order Taylor series expansions, where we want to try and capture these delta x. You can notice here that we are actually modeling uncertain propagation as relative motion, just saying, well, the same way that in relative motion, we have a secondary trajectory that we try to follow. In this case, we're going to have an uncertain distribution that we are going to propagate, but we can treat that exactly the same way. So with the Taylor series expansion, the first order terms, this is the transition matrix. We are using this tensor notation for the indices that actually comes from Dan Shears and Ryan Park. But we can keep going from this first order and start including, for example, second order terms. You see now that instead of a state transition matrix, we now have a tensor. So we have more indices, more fun. We could even go to third order, but also we are increasing the order of the expansion. This increases the accuracy, but also increases the pain of the analyst that when you have to implement this, yeah, it can become really, really cumbersome. Specifically because the dimension of the problem starts growing really, really quickly. So we need n equations for the state transition matrix, but then we need n squared for the state transition tensor of second order. There are some symmetries that we can exploit, but still there are a lot of equations there. So in the end, using these formulations in a systematic way, it's kind of painful. It's expensive also computationally, and oftentimes you lose the nice like physical insight that you get with the first order, because now we have a lot of terms, cross terms, coupling. So this approach is usually, I mean, it works when you implement it properly and systematically, but it can be a bit tricky to use. So what we are gonna try to do is try to approximate these state transition tensors, like capture the dominant part of the state transition tensor using DROM, basically using a regularized time and the concept of working with a fictitious time instead of a physical time. And that's what we're going to do in this second part of the presentation. We're going to try and capture those nonlinear effects that dominate the state transition tensors. So the way we can do this is the same way that we solve relative motion using Dromo. And it's by realizing that in the time domain, when we use time as an independent variable, we have this issue of, well, if we provide it to the next time, the perturb orbit is going to be drifting backwards if it's higher by a certain angular amount, delta theta. And then at a different time, it's going to keep drifting even more, and we have the secular drift that we talked about already. But now, if we move into, could be a true anomaly domain, or it's in general any fictitious time domain, where now the independent variable is an angle. The good thing is that when we propagate both orbits, well, they are still pretty much aligned. There's no secular drifting here, with the caveat that now they are at a slightly different time, right? Because it's either you trade angle or time. But the good thing is that if you're formulating the problem in terms of an angular variable, you don't see any secular drift. You can keep propagating with the angle as an independent variable, and yeah, you are given the state of the two particles at the same angle, and sure, they will have a time delay between them, but in terms of where they are at that angular value, there's no secular drift. The secular drift will appear when we try to correct this time delay, but before we do that, until we do that, we are fine. There's really no secular drift. And that's really the kind of the magic idea that Jesus had, and the insight that Jesus had back in the day when we started this. Because by doing this, you isolate all the instability to just trying to correct this time delay. And it's a pretty amazing concept, and that's what we are going to exploit now. It's also nice to see that this is kind of loosely related also to how in perturbation theory you try to isolate pretty much like secular terms, and you forget about the short and long-term periodic effects. So it's also like a nice way to isolate this intrinsic stability to correct the time delay. Just another very insightful thing from Jesus. And this paragraph here with the correction of the time delay highlighted, this is from the very first paper that we published on this. And the core of that paper was really the correction of the intrinsic time delay. So there's this sentence here, it says, to recover the sense of the solution, an additional correction is applied posteriorly to cancel this intrinsic time delay. So again, it was really fun to see how this concept actually came back from relative motion into uncertainty propagation. And just by looking at this, I believe this was the abstract of the paper. So how can we actually do that? Well, just to state here again this diagram so we can have everything we need to start working the formulation. The first thing we have to notice is that now these two states of the two particles are given at different times. So we want to actually account for that time delay, and that's what we need to correct. Let me see. I've gotten a chat message. Let me see if there's someone left. So yeah, we want to correct the time delay. And the first order way to correct the time delay is just to have another series expansion in terms of time. So this delta x theta, this is the, let's say, asynchronous solution. So it's delta x without correcting the time delay. And the time aligned solution that we see, it's computed by using this simple expansion here, where f is simply the time derivative of the state. So this is as simple as doing like a linear propagation with the velocity and acceleration, and that way we can correct the time delay. So that's like the linear approach to correcting the time delay. That is, I hope it's intuitive in terms of kinematically what we are doing with this correction. From this, if we see this correction of the time delay as a series expansion, we can very easily include a second order term And by doing that, where we have now the second derivative of the state, we actually capture these nonlinear effects the same way that when you propagate just a rectilinear motion, you can capture the terms from the acceleration by using this dt squared term. So that's what we're doing here, and we can capture, in this case, the curvature, because the derivative of the acceleration is going to give us this kind of nonlinear effect. And that way, we can actually start capturing the curvature of the trajectory by including this second order effect in the correction of the time delay only. This is going to be the key. Moving on, is that we compute the asynchronous solution linearly, and then we only account for higher order terms when correcting the time delay. And another blast from the past is this equation here is from a 2016 paper, and it's another relative motion paper that we had using Dromo but generalized to any regularized formulation. And you see that the equation of the correction of the time delay is exactly the same one. Just the notation is a bit different, so delta f is actually what I'm calling f here. But the equation is exactly the same. And what took me like almost 5 or 6 years was actually realizing that you can actually expand this to second order and get this green term. That's kind of the novelty of the presentation from today, compared to what we did back in the day for relative motion. So mathematically, what we are actually doing is that when you look at the true anomaly and you integrate it over time, this is the part that is going to give us the secular drift that we were talking about. And that also applies to the partials. So when you take the partials of the true anomaly with respect to initial conditions over time, and we call them gamma, these are also going to drift because it's the partials of a drifting term. So you are going to have the same secular component in there. So when you think about the state transition tensor and how you build these nested partials of arbitrary order P, these partials are computed with a constant time, right? Because the physical meaning of the partials is in the time domain. Even though if we want to work in the angular domain, we still have to keep in mind that the physical sense is actually in the time domain. So we always have to make the correction if we want to first work in the angular space. So that's what we can do by expanding these nested partials. So these are partials at fixed time. If we want to express them in terms of the partials at fixed angle, we need to include this correction, which comes from the partials of the true anomaly. But this is still like an exact identity. So you can break down these partials into this decomposition, and you still get exactly the same state transition test. We are just rewriting how the partials are computed. And the very nice thing is that these green terms are the only source of secular terms. So when you compute the tensors, the only secular terms that you will end up getting come from these gamma terms in here. The rest, for example, the partials at constant angle, this gives you only periodic terms that if you want to, you can neglect completely. So in the end, we can build the dominant part of the state transition tensor by retaining only this contribution from all the gamma terms up to order P. So this could be any order that you want in principle. And this way we are capturing the dominant part of the state transition tensor. That is going to grow like, and conceptually, this is going to grow like time to the P. That's being the order of the tensor. So over given enough time, that's the part that grows the fastest. So it's the one that is going to dominate your state transition tensor. Yeah, so that's what I was referring to. And if you wanted to, you could also retain other terms because this is like expanding a binomial. But we found that the most valuable part of this formulation and this approach, the most powerful thing, is to just retain the dominant term of the transition tensor, because that's the simplest and also the most important one. And here's an example of how you can capture the second order the dominant part of the second order state transition tensor, which to me I think is the best application of this formulation overall, just as a trade-off of simplicity and actually improving things relative to a linear approach. And the state transition tensor of second order can be approximated just with this very simple expression here, where you have the partial of the true anomaly with respect to the corresponding parameter now you're differentiating with respect to. Then you have the second term here, which is comes from the time derivative of the true anomaly. And then you have the second time derivative of the state. So we can start breaking this down. The partials of the true anomaly, this is just 6 equations. If you have a vector of dimension 6, so you need a true anomaly with the derivative with respect to position and velocity. And these are the only extra equations that you need to integrate numerically, as opposed to the 216 minus symmetries that you would need if you wanted to propagate numerically the second order state transition tensor. Next, you have in red this parameter I was referring to coming from the derivative of the true anomaly. The good thing is that this is known during propagation time because you have the radius of the orbit and the angular momentum. So you can trivially evaluate this term. There's really no extra compute needed for that. And finally, in green, we have the second order derivative of the state, which, yes, you need to compute that, but it's not that hard because given that this is the acceleration and the jerk, which is like I never understood that name for the time derivative of acceleration, but anyway, we have the acceleration and the jerk, and this time derivative of the acceleration can typically be computed analytically, especially if you already have the partials of your force model for computing the state transition matrix. Computing the partials, like the time derivative of the acceleration, is actually pretty straightforward. So again, if you have the propagator set up where you are already computing the partials of your right-hand side, adding this term is relatively easy. And the good thing is that here we are making no assumptions about the dynamics. So we could have any perturbation in our propagator, and this formulation still works because this is just looking at how the acceleration and derivatives behave, whatever the acceleration is. So with this, from now on, I'm gonna focus on like analyzing how this works. And before that, there's a quick example I wanted to show here for an analytic solution for rotational dynamics of an axisymmetric body, and this is comparing the error of the approximation for different orders. So here in this plot, we have on the horizontal axis we have time, vertical axis we have error, and this is the first order solution. So we just propagate the state transition matrix numerically and check the error. This is the second order. So this is we propagate the second order state transition tensor. We have an analytic solution, so we can do that analytically. And then these circles, they represent how well does the approximation that I showed in the previous slide approximate the second order state transition tensor. And what you see is that it's only initially that we have a small separation just because secular terms are still small and periodic terms that we are neglecting are actually still relevant. But then given enough time, secular term is gonna really dominate over any other term. And the approximation that we had works really well compared to the full second order solution. This holds true also for third order. We can take only the t cube terms, so effectively the same equation that I showed before. I also mentioned that we could capture intermediate terms if we wanted to, for example, t cube and t square. So this shows that if you add the t square terms, you improve things a little bit. But in the end, after enough time, t cube is good enough to just capture the dominant secular trend of these errors. So that was with a very kind of simplified toy problem. Now I wanted to look at actual numerical propagation of an orbit and see how propagation of uncertainty works with this simplified second order state transition tensor. So this is a near-Earth asteroid with generic perturbations. And the way this plot works here is that we have kind of a string of particles where blue squares represent the linear propagation, just with the numerically propagated matrix. The orange circles represent the propagation with this approximate state transition tensor. And then in green, we have the numerical propagation of each of the particles, so effectively like a Monte Carlo type of propagation. And I have them arranged forming a circle. This is just to represent like a kind of like the 2D marginal distribution of uncertainty on the XY plane. So when we propagate this for 2 revolutions, we already see that, for example, the linear approximation is just, well, trying to capture this. You could think of this as being the covariance matrix here, and it's the linear approximation cannot capture any curvature, any nonlinearity. So that's why you see it being pretty much like a rectilinear axis, whereas the second order approximation that we are proposing is able to really capture this curvature, really following the numerical propagation. So this is like saying that we capture the Monte Carlo results, and this only gets worse with well, worse for the linear approximation as we propagate more and more orbits. The scale is increasing, and yeah, the curvature keeps increasing over time, and we found that the approximation of the second order state transition tensor does a pretty good job in capturing at least the dominant side of nonlinearity. This is another example where we look directly into the propagation of the mean of the uncertainty distribution, and this plot here is literally showing the position error, where position error means the error in the mean. Kind of redundant, but this is the mean of the distribution of the posterior. And we have in blue what we get if we just propagate the mean with the state transition matrix, and then if we propagate it with the approximate state transition tensor, is the orange dashed line that is very well aligned with the uncentered transformation, which is another very powerful and efficient way of propagating uncertain distributions through nonlinear functions. The only caveat of the uncentered transformation is that you need to propagate pretty much 2n plus 1 times your state. So you would need to do, for example, 13 propagations to capture the uncertain distribution, whereas with the approach that we are proposing, you only need to propagate once with the extended vector to count for the partial anomaly. So there's a significant computational gain compared to the uncentered transformation. In this case, we found that it was about 10x faster, so 10 times faster. When you see the accuracy, it's very comparable to the uncentered transformation, and it's about 1, if not 2 orders of magnitude, at some points better than the linear approximation, simply because we are capturing the nonlinear effect that the linear approximation is otherwise ditching. Same for the covariance. When you provide the covariance, again in blue we have the linear solution, and in orange we're going to have the second order, and then the transformation on Monte Carlo. The one very important thing is that the linear approximation does not account for the change in the mean, whereas with the nonlinear approach we do capture that, which is a great improvement, and it's very close to the uncentered transformation and very close to the Monte Carlo propagation also. So qualitatively, it does a really good job at capturing the dominant effect of the nonlinearity in the propagation. So just to close with another LEO example, just kind of revalidating the results that we see same gains in different orbital regimes. This is the same 1, maybe 2 orders of magnitude improvement at some points in precision when propagating the mean, and the same very good behavior when propagating the covariance relative to the uncentered transformation and the Monte Carlo propagation. So now that we have a good method for propagating uncertain distributions, capturing nonlinear effects, the final step that we did was actually plug this into an estimation algorithm, so effectively extend the order of a Kalman filter. And with a linear filter, you pretty much assume that the mean of the tether remains the mean of the posterior, so you have a 0 delta on the mean, and the covariance is going to be proportional to the state transition matrix times the covariance. And in this case, with the state transition tensor, we are able to capture that nonlinear effect. This should actually be next, I believe. And then we are also being able to capture the quadratic effect of the covariance propagation by using the state transition tensor. And with this higher order Kalman filter, the very good thing is that we are able to pretty much match the performance of the unscented filter without the computational cost of having to propagate 2n plus 1 times the state for any covariance propagation that we need. So that's this final slide here, looking at a kind of a toy model, assuming that we have an orbiter around Europa with thermodynamics and different types of measurements. And we're saying in two cases we have here on the left, assuming that we have a kind of optical type of measurements plus range rate on the left and no range rate on the right, kind of the estimation type of problem. And then what this is showing is that it's comparing in green the extended Kalman filter that is having some issues to converge. And then in yellow, we have the UKF, the uncertain Kalman filter. And what we are expecting is that the orange line would match the UKF. And that's what we saw in the simulations also, saying that with this very simple way of capturing nonlinear dynamics, and capturing that in the uncertainty propagation, we can mask the performance of the UKF without the additional computational cost that we incur when going with the full uncertainty transformation. So just to kind of to wrap up how this works, it's again coming from this original idea from Jesús that you can capture the main effects that the state transition tensor introduces by propagating the partials of the true anomaly by working in this fictitious time space. In terms of the practical gains, this is simpler to implement than the second order variational equations. It's also much faster. You only need to integrate 6 additional equations instead of 216 minus symmetries. This is very much based on that initial work from relative motion with Romo that I mentioned in the very first slide. And with the moment you have a good uncertainty propagation scheme, you can immediately create an improved estimation scheme. And finally, I wanted to emphasize that there's really no assumption about the dynamics here. This is valid for any perturbation, any source of force model that you would like to have. So that's all I had for this presentation, and I just want to close by again, Jesús, thanking you for these many years of learning from you and collaborations and so on, and really say that Jesús for me is one of those persons that really changes your life. And I think there's been two really defining moments. For me, the very first one was when he was the one who said, well, have you ever thought of doing a PhD? And I was like, no. But he was the one who suggested the idea, and thanks to the great experience that I was having during my final project of in the carrera, not really master thesis, but like the old school thesis that we had in Spain. He asked that question, and I said, well, that would actually be great because I'm having such a good time doing research with you that, yeah, I would for sure love to spend a lot more years just working on this problem. So that was the very first one. And then the second one was coming to the US. It was really thanks to Jesús that I was able to come to the United States. And it was initially for 5 months. And now we have an American baby. So definitely another defining moment that, yeah, I can only thank you, Jesús, for all of these years. And yeah, wish you the best. Thank you.
Javi, can you hear us?
Yeah, I can hear you fine.
Perfect, because we have a question from the room.
Hi, Javier. Congratulations for being a father. And thanks for waking up so early to give us this wonderful presentation. Amazing work.
Thank you, Claudio.
It's good to see you. Just one question about your propagation, uncertainty propagation scheme. You say that is valid for any perturbation. I was wondering, have you considered like a close flyby of an asteroid with a planet? Because that scrambles up the uncertainty cloud quite significantly, and perhaps it could be a good stress test for your method. I don't know how far you went in that regard. I was just curious because I think it's very challenging.
Yeah, that would be a great test indeed. I didn't look into that. The main application was more on the estimation side of things for this, and it was really all like boring closed orbits. Yeah, so I haven't looked into that. It would be fun to look into a flyby and see how it works, how it holds up. Yeah.
Thank you again, Javier. And now it's time for Sí, puedes usar este o este, el que tú prefieras. Si te vas a sentar.
Sí, me voy a sentar un poquillo. Espero no gastar mucho tiempo. Well, first of all, thank you very much to all the people presenting the works in this workshop and the people attending, and many other people that they are not able to be here, like Yago, Oscar López Rebollal, or José Manuel Edo. It's very late, and I try to be so brief as possible. First of all, I would like to, in my first idea, it was to present here a small talk about the works in which are involved in this moment. There are 3 different works. I am working in the Lambert problem with Elena Fantino, and now I try to recover to Odey to involve in this new line of research. I am trying to get Neptuno in order to perform a magnetic capture with Juan San Martin, Professor Juan San Martin. And I am also working in a new exact solution of a very easy problem, but with Dromo. This is an exact solution. Unfortunately, I have no time to present all these things because last week my daughter Elena suffered major surgery, and I have to take care of her during these 2 weeks. All right. In any case, I would like to say some words, but I prefer to speak in Spanish. But don't worry, because Manuel said me that it is possible to share this presentation with the exact and the correct translation to English. No. Lo primero que quería decir es que sea donde yo he llegado, no he llegado aquí solo, he llegado gracias a la ayuda de muchas personas con las que tengo una deuda impagable. Quiero empezar por agradecer, por ejemplo, el trabajo de Amable Liñán, que fue mi supervisor de tesis, o del profesor Ignacio de Arriba, que junto con el profesor Napolitano fueron 2 pioneros de la Agencia Espacial Europea con los que yo empecé a trabajar. No puedo, tendría que hablar de cada uno de los que habéis presentado, empezando por Enrico, que me atendió maravillosamente en los años 97 en el Smithsonian y que me permitió durante un año obtener resultados que luego han mostrado que son ser interesantes. Y luego toda la colaboración que he tenido pues con aquellos señores que han sido alumnos míos, como Manuel, como Dey, como Javier Roa, como tantos otros que hoy no han podido venir por aquí, y sin la ayuda impagable de, por ejemplo, de Martín, o de Elena, o de Claudio, al que lo conocí precisamente en el Smithsonian, y que al final ha acabado en nuestra escuela, donde está haciendo un papel excelente desde todos los puntos de vista, no solo desde el punto de vista de investigación, sino también desde el punto de vista de docencia. Espero no olvidarme de nadie. Si me olvido de alguien, le pido directamente excusas, porque realmente hoy, digamos, cuando uno se retira, cuando te jubilan, pues las cosas te obligan, aunque no quieras, a mirar a toda tu vida. Es como cuando dicen eso de que cuando te mueres ves pasar toda tu vida en un minuto como si fuera una película, ¿no? Que siempre dice alguien la famosa frase esa, dice, joder, qué mala suerte, mira que morirte viendo cine español. Pues esto es una cosa ligeramente distinta, pero sí te obligan a hacer una recomposición de tu vida, ¿no? Para empezar, cuando te dicen, usted ha cotizado 44 años, 6 meses y 3 días. Joder, pues no sabía que había cotizado tanto, pero es así, ¿no? Y entonces, a la hora de mirar para atrás y de ver todo lo que ha ocurrido, pues hoy tengo que decir que soy un hombre que estoy profundamente agradecido a la vida por haber podido compartir con todos vosotros. La mayor parte de vosotros he trabajado con vosotros, habéis trabajado conmigo, pues momentos de enorme interés científico y también de enorme interés humano, porque yo creo que con todos hemos conseguido tener un lazo de amistad que supera también con mucho lo que es la colaboración científica. Entonces agradezco muchísimo a los que habéis organizado este workshop por haberlo hecho y haberlo hecho encima en mi nombre, de alguna manera por agradecerme en el momento en que me he retirado, pues lo que vosotros sentís, un cierto agradecimiento hacia mi persona. Os lo agradezco de todo corazón y me encuentro enormemente agradecido a la vida, como decía antes, por haber compartido y haber recibido el apoyo y vuestra colaboración, que ha sido en muchísimas situaciones importante, esencial. Y eso es todo lo que te quería decir. Muchísimas gracias por estar aquí de nuevo. And now let's go to have lunch, ¿no?